record now. Not TV, just voice and data. So we're recording. Okay. This is, I think, guys, if you do grounding and bonding, and I apologize if you're a residential guy or gal. I don't think we have gals here. I can't see. If you do residential, that might be a little bit above what you're experienced with, but it's a good thing to do. So I'm going to start, guys, with, you have that sheet in the front of you. Let me show you how to go over this sheet, basically. And then we'll go a little bit more details. I'm going to try to make it fit. That's too much. Let's do 40 here. Okay, and then I'll zoom into it as needed. Okay, so and again, just I really apologize. They don't allow us to come in here. When I do these training classes, I always come 1 hour early. You sit up, you get yourself ready, but they don't allow you to do that here. So we're scrambling to catch up with time here, and you forget things when you're under pressure. So, okay, so, and again, I will zoom into this one. I'm going to go right in here and just walk you through. If you guys start from the top here, and I'm going to look at you because it's, okay, if you start from the top, this is your utility transformer coming over here. Typically, we're talking about three-phase system, right? This is three-phase, big power system. So if you look at the top here, you have 13.8, I believe I have the voltage here, primary delta typically, coming into 480, 277. And typically, the system that comes to you is Y grounded system. So the utilities will take your neutral here and they ground it. They have a ground rod at their transformer. So everybody understand what this block is? This is the utility, the service. The service coming to your buildings. Cool? Now from the service coming to your building, I have, it's a 48277. I'm coming into CT cabinet. You guys familiar with the CT cabinet all the time, or termination box. So you're coming into the CT cabinet here, or termination box, where you can meter your power that's coming into your building. And we'll see how we'll bond and ground around this one. Then from the CT cabinet, that could be on the wall or another box on a pad-mounted box. You're coming into with your 48277, coming into your switchgear, switchboard, or panel board. Typically, right? That's what we bring in a major power system. So that box here is my switchgear, switchboard, panel board, MCC, any service entrance equipment. We call them service entrance equipment, right? Cool. And what is that? So that's my box. These little things supposed to be the conduits, guys. These little things in between, these are the conduits. So that's my service. From my service, I'm going to want to just give you the big picture. I took a feeder and I fed a transformer. This will be a 480 delta Y transformer. And from that transformer, I derived the neutral, the white neutral, and I fed a 28120 panel. Typical in every commercial building, guys, respected commercial building, you want to have two voltages, right? 480, 277, and 28120, right? That's the separately derived system, transformer separately derived system. So I took a feeder and I fed this transformer. From the transformer, I fed typically 225 amp panel, 300 amp panel, receptacle panel. Cool? If you're familiar with that brand, so that's a feeder coming through the transformer. Then, the reason why I picked these for you guys because each one of them, remember we're talking about ground and bonding. Each one of them has special characteristics and rules for grounding and bonding. I didn't pick a transformer just because. This is your separately derived system. Okay, so everybody goes, here's my feeder, transformer, through a panel, separately derived system. If you come to this side, I picked another panel that could be another 2000 amp switchgear, switchboard fit from a 4000 amp switchgear, or it could be a 60 amp panel fit from 100 or 200 amp panel in your garage. So it goes from wherever you want to go. So that's that sub panel. The only difference for this sub panel is inside the same building. when the panels are inside the same building, there's rules and regulation for bonding it and grounding it, as all of you probably know that. Then I took another feeder, and I feed another panel, and this is also another sub-panel, but this sub-panel is in a separate building. So you have building A, 4,000 amp switchgear, feeding another building B with another 2,000 amp switchboard or switchgear. Or it could be a 200 amp panel, residential 24120, feeding a 60 amp panel in your shed, detached shed, or typically detached shed, or detached garage, or detached structure that you have in your building. So this is what we call a separate structure or separate building. The reason why I picked that one, as we all know, because if you go to a different building, there's rules and regulation for bonding and grounding for a separate building. Okay? So then, to spice it up, I threw a generator at the top here. If that's not enough for you, we threw a generator, and we grabbed my generator here, and I pulled the neutral from the generator, and I have, I think I ran it as separately derived system. So separately derived system. So I have another generator that I'm running it as separately derived system. I'll say a few things about generators when we come. Generators, you have an option. You can run separately or not separately, and I'll say a few things about it. This is separately derived system generator. We're going to bond and ground at the generator, and then we're going to tie it into the switch gear. Cool. Okay, so that's kind of the big picture. And right in here, that little grounding bar. If you did a commercial building, typically a big grounding bar will be in the electrical room, and where you bring all your grounding electrode system into this bus bar, outside cover bus bar. Typical, you don't have to do that, but if you have a bigger system, that's really cool to bring in. So this guy is going to collect, imagine this bus bar is a collector for all your grounding electrode system in the building. So, and all these little things that's going down here, they're going to a water pipe, the steel of the building, they're going into the ground rods, they're going into grounding electrode, conductor ground ring around the building, and all the approved a grounding electrode system in your building. You can collect them all in one bus bar and bring them into your switchgear. Does that make sense here? That what this chunk of stuff here? Any comment, guys, about the big picture before we get into a little bit more details? Because it's nice to see.
Internal of all your equipment?
This one could be internal. Typically, it's external. Typically external. Yes, absolutely. This is external. And it's actually better to have it external. I'll tell you in a few seconds there. So here's my collector of all my ground electrode system. And then right at the bottom here, guys, I did the same thing. Can you guys see that? It's another collector. I call it collector of my grounding electrode system. And the reason why I have this one at the bottom, because I have moved into a separate structure, and the code requires you to do the same thing. You move to a different structure, you have to create a new grounding electrode systems and bond your equipment into that system. Any question about the big picture before we go into the details? The devil is in the details always, right? Does that make sense, guys? Is that what you see? The only thing that's not, and this will represent, and please correct me, all of you guys are masters and journeymen and engineers, that will probably 80% of what you need about grounding and bonding in typical buildings. The only thing that's not here, as I stated, is agricultural building where you have to have ground equipotential plan, and you have swimming pool with their bonding the belly of the swimming pool. Hospitals, a little bit of you bonding the panels to the hospitals. It's not here, but that's, as I said, represent probably 80% of what you need in a typical commercial industrial building, from a 200 amp 24120 service all the way to a 4,000 amp 480 or 28120 service. Any comments, guys, about this? Did I forget anything that you guys dear to your hearts that's not here? Now, in order to get all this, you have, I'm not kidding you, all this that you can see summarized, literally 13 chapters out of 20 chapters here. All the 13 chapters summarized in one sheet. So, And I thought it's really nice to see 13 chapters in one sheet, you know, right? You don't really didn't get into the details of that. Okay. Any comment, guys, before I move in and dig a little bit deeper into it, into the system?
The grounding bar is the ground rod, the water system.
Absolutely. The grounding bar here, that's a collector, and to it you collect your the water. The grounding electrode system has a water, ground rod, what do you call it? Steel of a building, concrete encased electrodes. What else did I forget? So ground ring. All these you collect them into that bar, and from there you take them inside your switch gear, or you take it to a lot of places.
Transformers are delta Y.
And my transformers on the which one of them? Okay, the feeder. Yeah, this is a delta Y transformer. This is a delta Y transformer. If it's a delta, I've never. Do you guys have a delta service to a building? Anybody have seen a delta service to a building? A delta to a building? Typically, did you guys?
Our older buildings had that. Yeah.
Okay.
Not-
Is it center tab though?
No, it was a corner grounded system.
Okay. How did you get your 120 then? You created another
Well, they had transformers all over, but yeah, the incoming was the delta.
delta corner grounded
Part of
system.
the building.
Okay. So typically, guys, good point. Typically, Excel will give you a delta Y grounded transformer. For anybody knows why? I mean, you can utilize number one is safer. Number two, also you can utilize two voltages. If they give you delta, you lost 277 or 120. So from a utilization point of view, a delta Y transformer is superior. It gives you two levels of voltages. So then you can burn your equipment, the high power equipment at a higher voltage, and the lower power equipment like lights at 277. Does that make sense? So now, with this change, if it was a delta, few things will change. But really, the bonding and grounding, other than there's no neutral in a delta, that's it. Ungrounded system, there is no neutral. Everything bonding and grounding will not change if it was a delta or a delta Y. The only thing that will change is there's no neutral, then you are not going to bond something that does not exist. So there's no bonding to the neutral, right? If you have no neutral, there is no bonding to the neutral. And that will eliminate two things. Main system bonding jumper and main bonding jumper. These will be eliminated if it was a delta transformer. Any one of them, the top or the bottom. Yes, sir.
If you have a delta, you still got to carry a neutral inside whether you use it or not.
But you don't have a neutral if you have a delta.
Well, you got to carry a wire inside it.
If you have a delta, if you have, and the code says if you have a grounded conductor, if a system is grounded, the only time you have a grounded conductor, aka the neutral, is if your system is grounded. If you're getting a delta, the only thing you will carry from the transformer here up to your building is really three-phase conductors. That's it, by code. You don't have to carry the neutral, because the neutral does not exist. You know what I mean? So that's kind of any comment, guys, any question? I know grounding and bonding is a live topic and cool, and everybody has their own issues about it. No? Don't you guys think so? Any comment, guys, any questions about the big picture? So I'm trying to summarize, like I said, 13 chapters in one big picture.
What do you mean it could be or couldn't be separately derived on the transformer? Or on the generator?
On the generator?
Separately derived, or it may or may not be. What do you mean by that?
Can we let that one go
Yeah,
later?
fine.
Yeah, I'm coming to it. That's a whole different topic. Are you going to make your generator, separately derived system or non-separately derived system? I'll give you a couple of hints when we reach a generator. Any comments, guys? Am I missing anything about, like, we talked about delta. Anything here is missing? Yes, sir.
Confusing me because they have weird delta centered around, and then you have a wild leg.
Oh, that's a grounded delta.
Yeah.
That's a grounded delta. Yeah, you're absolutely right. That's a grounded system. That's not a delta. A grounded center tap, grounded delta is a grounded system. It's not a delta. Delta is an ungrounded system. Yeah. Or center open delta, center tab. These are all grounded systems. Good point. Any comments, guys, about the big picture? So everybody knows what we're trying kind of to achieve. Shall we zoom in a little bit? and get into the bread and the butter of that. Okay, my first zoom in. I'm going to just zoom into the utility transformer and get you how they bond and ground there. Oh yeah, I forgot to tell you, because anybody can draw a good diagram and put good numbers on that. So you don't think that I brought these numbers from my basement. I always say, if you can say anything you want about the code, but you have to substantiate your opinion by referencing the code, right? So I'm trying to substantiate my opinion with everything that I tell you here. And if you look at the second 2 pages, you guys have how many pages? Yeah, it's a front and back. One of them is front and back. If you guys look at the front, so all these wires are numbered for you. I numbered them, and I did an example for you here, how to size them. And I referenced in the NEC code book, where does it talk about them? So, so we're all the same. And again, it's my understanding. Please correct me by any means. I'm like you. I understand the code certain ways based on my reading. If I made any mistake, I really, really appreciate if you guys can bring it to my attention and no hard feelings. Cool? I'll buy you a cup of coffee if you bring something, because we correctly will learn, right? So here's the sheet 1 and sheet 2, guys. For yours is basically calculation for this system that I'm going to show you. The red, you can see the red. You guys don't have a red. If you need the colored one, I apologize. I told them to make it colored. It seems they're trying to cut and cost a little bit. The red stuff is an example. The black stuff is what the code says and the references and explanations. The first column is what the name of the grounding or bonding conductor is. The second column is how do you size it? And the third column that you can see is where does it say that in the code? Does that help a little bit? Substantiate what we're saying. And again, we're summarizing 13 chapters, so be patient. It's a big picture. Look at the big picture. When we did it, guys, if I start you with talking about grounding conductor, we spend literally 2 hours talking about grounding conductor. By the time we're done, you don't see the big picture. So I like to start with the big picture, and then we zoom in on certain areas. Any question, guys? Any comments about the whole big picture before we go into it? Yes, sir.
On the second page, what is MBJ and main bonding jumper?
Yeah, they're coming down. They're defined. Yeah.
Okay.
They're,
There we go. Yeah.
yeah, they're all defined down, guys. All of them are defined at the bottom, and so let me just zoom. Maybe I'll zoom a little bit here, 100. So let me just take you, for example, to. Can you guys see that gray conductor, number 1.0? Where's my pointer? You can see that conductor. That here both of them is called 1.1, and this is also 1.1 connected to N for neutral. ABC is for the phases, right? Phase A, B, and C. So if you go down, so watch what happens when you go to N. How do you tie the two together? You go all the way to the bottom. Here's number 1. Number 1, my friends, it's called grounded conductor, aka neutral, and N is the symbol that I'm used for it. Cool? And then service equipment. I wrote here service equipment. And then I give an example of how do you size the neutral. I'll go in detail a little bit. How do you size? MPG is main bonding jumper, and it's also referenced down there. And then based on power system unbalanced load, not smaller than the main bonding jumper. If parallel, you can't pull more than 1 knot. So summarize kind of the rules for sizing the grounded conductor. And where does it say that? So you guys don't yell at me and say, Chad, you brought this one from your basement. Here's what it says, all this stuff about the grounded conductor on these articles. And I would hope you guys will go there and reference them. Does that make sense? At least how it's built, the whole system. Cool. I know engineering firms, guys, they have a lot of, they don't go deeper. I don't know if, when I work for LB Beckett, they really care less about supply side bonding jumper for the most part. Main bonding jumper, they don't care too much about the equipment bonding jumper on the load side. At least our firm. I don't know if anybody work for engineering firm. Do you guys size the equipment bonding jumper on the supply side and the equipment on the load side? Engineering firms. If you work for an engineering firm, they typically depend on you guys to size the electrician, the contractor to size, unless you're a contractor who has engineers in house. They depend on you to size the equipment bonding jumper on the load side. Do they tell you what type of fittings you have to use on the service? That's methods and material. I always, guy here from Shed Pool Erickson is a friend of us. He always say, if anybody dealt with him, he always say, methods and material is not us, Chad. That's the electrical contractors. You have to come up with the methods and material, bonding, grounding, and all the wiring methods, and how far you stable your conduits and so forth. So my point is, this goes a little bit further than what we do as an engineers in terms of providing things. A little bit further in terms of grounding and bonding. So, okay. Any comments, guys, about just the big picture? I keep saying the big picture here. Okay, so see how how the system is laid out. I'm going to start with the example that I have. I said I don't know where to stand here without getting it anybody's way. Here's a typical example. It doesn't have to be this way. Typical example. You have a hospital or government building. You have a stadium, and you start with typically 13.8. You guys are familiar with 13.8 system. A lot of places have 13.8 now. They have 4160, but not a whole lot of places use 3160 anymore. They upgrade to 13.8. You have 13.8 primary coming as a delta from Excel or Minnesota Power here or whatever your utility is, to a transformer provided and by the utilities. And that transformer typically is Y grounded, like you can see. And you have your neutral and the ground bar. They're bonded together, and they drive a ground rod typically right by the transformer the utility have, right? Do you guys see it differently? And we, as contractors, have no control over this system. We have no interface with it. We don't deal with it, right? Do you guys go there and ground the transformer for Excel? You know, we don't really ground the transformer for Excel. Be it pole-mounted transformer or pad-mounted transformer. We don't get into that system. Okay, so and it's color-coded. This is supposed to be your brown, by the way, and this is your orange and yellow, and this is supposed to be the gray, right? Isn't that the typical, not code required, but typical industry standard for 48277? I don't know if it looks like brown here, right? So I apologize for you guys. Yours look all one mess of a color here. Okay, any comments, guys, about bringing the service to the building? So the common mistake, guys, when I teach electrical design and when I do training is a lot of contractors and engineers wants to pull an equipment grounding conductor from the service here into the transformer, and they always to the service. So this is service entrance conduits coming in here. They want to pull an equipment grounding conductor. Not required. You can if you want to, but Excel does not allow you to take it. So between the transformer and the termination box or the CT cabinet, you're really pulling three conductors, typically pulled by Excel or whatever your agreement with them. So they come from a transformer into your termination box. This is called CT cabinet or termination box. This is, you guys provide this, right? The electrical contractors, pad-mounted transformer, pad-mounted box. Typically they have the bars, the CTs, so you can monitor your system. Or it could be just a termination box where you can terminate, you can interface with your system with Excel. Anybody knows why we have the termination box? You guys remember why the termination box came to be? You know the story about that? So the engineers come over here and size a 4,000 amp switchgear. And with 4,000 amp switchgear, you need 11 runs of 500 kCm. That will get you there if you use 500. So take 5 sets of 3 conductors plus derated neutral, 11 sets. 11 sets of 3 phases and derated neutral. Take them from here into the transformer. The problem when we go to the transformer, guys, not enough lugs to land these 11 sets. Have you guys been there? Yeah. Conflict, clash. That's called the clash of civilization between us, the engineers who work in the construction business, and also us, the engineers who work for Excel. Excel does their calculation, and power companies are completely different. They do it based on, when they size their transformers, I'm sure you guys are familiar with that, they size it based on statistical data. They can tell you, it's all the numbers that you submit to me is horseshit, basically. We have data. For us, we have data to prove that your building, no matter what you put in this building, is not going to take 4,000 amp. They have data to supplement it. Why? Because they powered hundreds of hospitals, nationwide or wherever the jurisdiction is. So they have statistical data that they can depend on. So when we, as engineers or contractors, when we provide them with a load calculation for our hospital, they look at it and typically they apply a service factor, a demand factor, between 50% to 70%. So if I ask you a 4,000 amp switch gear, the engineers will look at it and say, yeah, we know statistically that's not really what they want. We're going to go apply a load factor of, say, 50%. So they give you a transformer worth of 2,000 amp when you're asking for what? For a 4,000 amp transformer, or say a 3,000 amp worth transformer. So what's wrong with this? Nothing wrong, except when you try to terminate a transformer rated for 3,000 amp to a switchgear that's rated for 4,000 amp, they don't match, not enough lugs. So we came up with that termination box, right? Am I right on that? Everybody had this experience before? So that's the whole termination box that came to be. So from here, Excel will bring as many cables as they want based on their feeders. And we bring this, we size, so this could be 11 sets of 500, and here, coming from this transformer, it could be 8 sets of 11 sets of 500, this could be 8 sets of 500. And the interface on this termination box, and we size the termination box based on the worst scenario, which is 11 sets, everybody's happy, right? Any comment, guys, about this one? Any comments, any questions? Now, if you're a residential guy, this probably you don't deal with that. So that little deal here, just drop it. Imagine this does not exist, and you pull your neutral all the way into your service, right? That's the only difference. The meter, it goes into a meter. This will be your meter socket if it's up to 400 amp or less, I believe. That's when they start putting it. So 200 is very typical. 200 amp meter, that will be your meter socket. Think of it as. Any comments, guys, about these two coming in? Okay, so I came. Now, what do you do here in this box? Typically, what we do is we bring the neutral. And do we have to bond and ground? Do we have to drive a grounding conductor? You can if you want to. We are on what's called the line side of the service disconnect means. On the line side of the service disconnect means you're allowed to ground the equipment using the neutral, but use it sparingly. Right? That's what the code says. Does that make sense? So this box here, what's going to ground this box? What's going to ground this box is a neutral. Is it wrong if I went here and I drove a ground rod right here and ground a neutral? No. There's nothing wrong with that too. But the code allows you right in this box, here's my neutral. Your neutral will be basically bonded. Your neutral right in here will be bonded to the box, to the termination box. Why can we do this? Because we're on the line side of the disconnect. Where's the main disconnect? Service disconnect. Service disconnect exists in this 4,000 amp switch here. Does that make sense? Do you guys do it differently? Anybody drive a ground rod right by the neutral and ground it right there, the termination box? You guys do that? It's very clear in the meter socket. In the meter socket, do you go drive a ground rod in the meter socket and another ground rod that goes to the pan? You can't ground in the meter socket. You're allowed to ground in the meter socket, ground the neutral, but then you don't go in the panel and ground it again. Typically, you ground in one location in the panel, where the service disconnect means reside. Any comments, guys, about this? Is this too much, by the way? Yes, no? Were you that quiet yesterday with Paul? He said you guys were talkative and all this time? Yes, sir.
I had a discussion yesterday with Noel, retired distribution area engineer, about exactly that topic, about sizing service transformers for building services. And his experience is exactly what you said. Never listen to the electrician what he thinks the load is.
Yes.
It doesn't work.
Yeah.
And he said we'd be putting up massive quantities of massively large transformers.
I worked for a company called as an engineer, Associated Consultants Engineers. They used to be in Plymouth here, got bought by Short Elliott Hendrickson. If anybody works with Short Elliott Hendrickson, they build wastewater treatment plants in the Midwest. Anyway, we used to do that exactly the same. We are the representative of small towns, distribution system, 13A to 69. And we used to look at, I was on the other end. So we take the calculation for the building and we call it architectural, not even engineering load calculation. We call it architectural load calculation. And then you apply, like I said, a demand factor of 50 to 70 based on the type, hospital, whatever, and based on the statistical value that you do, and you size your transformers. And they're absolutely right, guys. You go into a switch gear that you size 4,000 amp, and you look at when everything is humming and up and running, you look at the switch gear is pulling 2,000 amp, right? Anybody size a 4,000 amp switch gear went there and found like 4,000 amp pulled out of this system? And do you guys know why? A couple of reasons. You know how many 25% we up before we reach the service? That 25%, the safety factor. So just imagine, every conductor, every panel that you do, we throw a 25% on it, extra. And because we don't have, they don't make standard transformers, so if you end up with a transformer that's not a standard, what do? You go up again, right? So imagine how many ups and ups we go by the time you reach the service. Your demand load actually is probably 50% of what you size for. So they are completely right. And they have the numbers to prove it too. We don't have the numbers. I don't collect numbers about hospitals nationwide, and I can argue with people. So anyway, any comment guys about how the system is put together here? So now from the termination box, the CT cabinet, the meter socket, that could be a meter socket, termination box, CT cabinet, any of these. From here, you pull the neutral only. You bonded the neutral to the frame, so you can ground the frame of the box. You must bond and ground the frame of a box, the termination box. Then we enter the switch gear. When we enter our switch gear, how many conductors we're pulling for three-phase system? We're pulling 4 conductors. If your system is a delta, you're pulling 3 conductors. Delta ungrounded, you're pulling 3 conductors. The only thing that's going to drop that gray one. If your system is 208, guys, would that be different if your system is 208 system? No. If your system is 240 single phase 120, would that be different? The only difference is you're going to be pulling 2 conductors and a neutral, right? If this system was 240 120 3-phase system, 240 120 3-phase system, that's a delta center tab system, right? They give you a 3-phase system. They tab one of the phases to give you the neutral. Your conductor will look exactly the same like this. As a matter of fact, just to go a little bit higher, if this transformer was 13.8 and the secondary of this transformer was 4160, high voltage, still the same. If that transformer was 13.8 coming to 4160, it's still the same, except when you go higher, anybody does higher than 600 volt? Do you guys size higher than 600 volt? The only difference in a higher than 600 volt, if your system is grounded, you do not need to bring the neutral conductor into the service disconnect. So your neutral conductor here, if that was higher than 600 volt, does not need to enter the service unless you're using them. And typically for building, we don't use the neutral. So when you take 4160 to a hospital, you really don't use a neutral, right? We don't use 2400 volt. We take the 4160 into primary of a delta transformer, transfer it back at the 13th floor of the hospital, right? Take it all the way to the 13th floor, transfer it down to 4160, 480, 277, and we feed all the chillers and the air handling units and cooling towers and so forth. Okay, any comments guys about this? I don't know if I told you guys I have 2 speeds, one fast and one faster, so you have to slow me down. And when it's time to break, please let me know because I tend to keep going. I always joke with my wife, I said, honey, at Dunwoody, they pay me to talk and they listen. At home, I talk for free and you don't listen. We're recording here. That's the problem. Okay, let's go to the service. So we brought the power. Does the logic make sense, guys? I started with the transformer, bringing the power to your building. Now we're in the building. We enter the building. When you enter the building, these are conduits. When you enter the building, let's say if you enter with a rigid metal conduit. I brought rigid metal conduit, corrosion-treated rigid metal conduit between my CT cabinet that I control into my building. Cool? You can bring PVC Schedule 80, right? Typically PVC Schedule 80 or rigid metal conduit inside. We're underground. We're coming underground. If you're underground, PVC Schedule 80 is your conduit of choice, right? If you're going above ground, you use rigid metal conduit. If it's steel, it has to be treated for corrosion if it's underground. Okay, so here's my assumption. This will be rigid. Why it's rigid? Because it's metallic. What do you do with metallic? You bond. That's why. If it was PVC, you just don't bond, right? Do we bond non-metallic stuff? Not in the low voltage. In the high voltage, guys, non-metallic, you'll be shocked if you know what happened if you have a non-metallic object in say 69,000 volt system. The non-metallic accumulate charges, right? And what happened if you get zapped by a big charge from a 690? You get killed. So sometimes they connect, they drain the non-metallic just to drain the charges from it. So there's other issues. Luckily, 600 volt or less, we don't have to worry about that. So we don't ground the PVC. Okay, we're inside the switch gear. We brought our 277 in neutral. We brought our three-phase 480-277. Now, the first thing we do is switch gear. You're going to have two, or any panel, you're going to have a bus bar, 3 bus bars for the phases, horizontal or vertical, depending on your switch gear or switch board or switch or panel board. You're going to have a neutral bus bar and a ground bus bar in the bottom of your switch gear. If it's a 200 amp panel, you're going to have them the same 2 bars. The first thing you do there is number 2. Number 2, this is called main bonding jump. Cool? Everybody understand that one? Number 2 here, that's a piece of copper or aluminum that you take, or it could be a copper bar inside your switch gear, and you bond your neutral to the grounding bar. And in turn, also the neutral will be bonded to this ground bar is bonded to the frame. So the ground bar will be directly bonded to the frame of the switch gear. And we take my neutral and I bond it with that green till you see that little number 2, and I bond the neutral. You do this at every service if the service is a grounded system. If the service is ungrounded system, there is that number 2 does not exist, right? Any comment, any questions about number 2? Any comment, guys? Any questions about number 2? That's the bread and the butter of basically grounding and bonding. You take the neutral and you bond it right to the service. We all know that, right? It's not. Now we bonded the neutral right in this here. Okay, everybody knows that. And then you have your ground bar here. I'm going to go to from your ground bar. The code says if you have your service in any building, you have to have at least 1 grounding electrode system. What's a grounding electrode system? A metallic object in direct contact with Mother Earth. Think of it. So the code says if you have any system, grounded or ungrounded system, you have to provide a grounding electrode system or systems, so you can bond your frame of your box, including the neutral in this case, into this grounding electrode systems, right? Okay, so one way of doing it is to grab this cover bar right here, grounding bar, and you take this conductor number 3 is called grounding electrode conductor. Grounding electrode conductor. When it comes to grounding, guys, terminology is very important. If you say grounding conductor, it's meaningless. You have to put a lot of adjectives. So it has to be grounding electrode conductor, or you go find it in the code. You don't know it. If you go grounding conductor right now, you can't find it in the code. They got rid of it actually in 2011. It has to be equipment grounding conductor, grounding electrode conductor, main bonding jumper, system bonding jumper, supply side bonding jumper. All these terminology, you have to use the right terminology so you can find them in the code. So this boy here is grounding electrode conductor. We take it into the bar. We're not talking about the sizing yet. And then right to this bar, I bring, let's assume this one was my water pipe, tie into it again with a grounding electrode conductor. Then I go to, let's say this is ground rod. This is the steel of the building. This is a wire, like a wire ring or ground drain. This guy is supposed to be a ground plate. Anybody have used ground plate, cover plate to supplement your grounding? Ground plate? Oops, where did it go? So these are all the grounding electrode system, and I forgot what that was. What else did we forget about the approved grounding electrode system?
The U for ground?
U for ground, yeah. Concrete encased electrodes. Concrete encased electrodes. So these are or any other object in direct contact, like a big tank, not a gas tank, big tank buried underground for water or something, that qualify as a grounding electrode system. So you group them all together to a bus bar, and you bring them to the switchgear. Now, can I bring them directly to the switchgear? Yes, you can grab them. Why this would be a good idea to group them out, guys? Because you can have, if you bring this one to the switchgear, what happens if you open the switchgear? Every time you open a humming switchgear, what do you need to do? Well, yeah. When you work in a switchgear, you have to put the switchgear in a safe operating condition or working condition. Safe working condition is you lock it, you tag it. Really, you're going to shut down the whole hospital, lock and tag and work on it. If you have a reason not to lock and tag and work on it de-energize, you have to have a reason. OSHA says you have to have a reason. Not like inconvenience is not a reason for working energized, as we all know. The reason would be I can't shut down the operation room in the 3rd floor. Somebody's chest is open. That's a good reason, right? Wouldn't you think so? So for that reason, then you have to put the PPE, the proper PPE. So you have to put your PPE and work on it. So do you really want to go torque anything here and go, you torque these one, you're going to go work on it hot. So that's an advantage of having everything, these stuff outdoor. Because they are now hot, you can torque them, you can work on them, inspect them without being dressed up in category 4 in this switchgear. Any comments, guys, about this? Any comments? So that's, you guys are all familiar with that one. Now, and so that's my neutral. Then I'm going to go to my rigid metal conduit coming. If you're familiar with the switch gears, guys, and switchboards, I'm sure a lot of you, if you did anything higher than 1200 amp, 480, 208, 480 or 208, you're dealing with switch gear or switchboard design. These are standalone, are either against the wall or right in the middle of a room, and bottom is open. Right? When the bottom is open, imagine bottom is open and you're bringing 11 sets. In this case, guys, I'm bringing 11 sets of rigid metal conduit. Say 4-inch maybe, the size, we haven't decided it. 4-inch rigid metal conduit to the bottom of switchgear. What do you need to do with all these conduits? Bond them. You need to bond them. So that number 4, can you guys see that little thing here? This is so-called supply side bonding jumper. Supply side bonding jumper. In the past, before 2011, there used to be equivalent bonding jumper on the line side of the service disconnect means. Now remember, my service disconnect means is sitting right here. I'm not showing the service disconnect means. So number 4 is what we call a supply side bonding jumper. You guys are familiar with supply side bonding jumper? Supply side bonding jumper? Okay. Now that little black dot that you're looking at, that could be anything that you can imagine. That could be a grounding bushing. That could be a hop, a threaded hop. Well, in this case, we can't have a threaded hop if you're coming underground. A grounding clamp that you take your conduits, you put a clamp around them, and you ground them, right? So the process, now you guys are electricians, the process that you do that one, grounding bushing, grounding log, because we're the service, grounding bushing, grounding log, grounding wedge, not on the switch gear though. If you're like a panel, you have a grounding wedge. So these are typically the stuff, we're going to look at a couple of pictures later on. But that's for you guys because you are methods and materials. The easiest thing, guys, is a grounding fitting here that you put with a grounding jumper, right? And you grab that wire and you tie it to the ground. That's typically the easiest way that you do at the service. You can have a grounding clamp around the conduits, clamp, right? And you tie it. Any comments, guys, about this material, the dot that this material is in? So I grounded all my conduits. How do you do that, right at this point? You have two options. You have 11 of them. Right? You 11 conduits coming from the bottom underground. How do you guys do it? You daisy chain them. Yeah, you can do two methods. Either you daisy chain them, you take one to the other to the third unbroken daisy chain, right? Daisy chain 1, 2, 3, 4, 5, 6, all the way to 11, and take it all the way back to where? To my grounding bar inside the switchgear dot. That's, I think, the proper method. The other method, if you like to terminate and cut wires a lot, is you go one conduit at a time. You take the first 4-inch rigid and you ground it to the grounding bar, and then the second, and then the third home runs. These are home runs. one from every conduit into the ground bar. Anybody does it this way? The code allows you to do it. Either way, any method. But typically what we do is we group them all together. Any comments, guys? Any questions about this? Comments, questions? Does it make sense? No? Am I beating a horse that you guys know? Or okay. All right, so we got that. We got the grounding. Now I'm going to go with this. I'm just going to go flash the calculation that we did. I want to remind you guys, my assumption here is I have a 4,000 amp switch here. So I'm sizing for a 4,000 amp switch here. It is sized for a 4,000 amp switch here. So I'm going to go down and size a neutral for a 4,000 amp switch here. So just quick here. Okay, number one was the grounded conductor. And you can see that's a grounded conductor, number one, coming to the service. Okay, here's what the code says when you size number one. We need to size a grounded conductor for a 4,000 amp switch here. Right? Anybody size a grounded conductor for a 1,000 amp switch here? Two options. Option number one, full neutral and colored HAT. Engineers love that. We don't pay for copper, right? You guys are contractors. Every time you cut your copper is expensive. If you can get away with lower copper, and utilities tell you all the time, the neutral not carrying a whole lot of amps at that level. So here is the minimum that you need to start. Always start with the minimum. The minimum by code that you size your neutral for your 200 amp panel or your 2,000 amp switch gear or your 4,000 amp switch gear. Doesn't matter. The minimum that you go by is, my friend, is it cannot be here based on the power system. First, the rule is if you know the unbalanced system, you size it based on unbalanced system. Now I do a lot of calculation for commercial, residential, and industrial building, guys. But because I'm an engineer, I have a lot of Excel sheets. If anybody wants some, I'll shoot it your way too. So, it's really hard to predict the neutral at that level, at the level of 4,000 amp. By the time you reach the level of 4,000 amp switchgear, guys, remember all your lighting system has been balanced. All air handling units, all your mechanical equipment, HVAC equipment, heating, cooling, and ventilation equipment, all of them are three-phase, do contribute big fat zero to your neutral, right? So by the time you reach a 4,000 amp switch gear, the neutral size is substantially small, substantially. Just because you dropped, imagine, all your HVAC equipment dropped. All of them are three-phase, right? They don't carry neutral, for them, almost all of them, right? So HVAC, and that's what, 30% to 45% of your load in any building at any time is heating, ventilation, and cooling equipment, right? We have light, another 30% of light. The light will be 277, balanced, right? So you balance your loads, and then, so that will be a neutral load. Receptacles will be a neutral load, but they will be reflected on the primary side as 480, also balanced three-phase. So long story short, I'm not going to convince you. Please raise your hand if you disagree with me. By the time you reach that level, the neutral load is not a whole lot. So the unbalanced almost dropped that one. Not smaller than main bonding jumper. And if you parallel, do you guys remember the rule for parallel? Now I'm paralleling here. Can you parallel less than 1 aught? No. Can't parallel power less than 1 aught. That's the minimum that you can parallel. Everybody knows paralleling conductor, right? If you want to carry the load with two conductors, typically, if your conductors are larger than 500 kcm or your load is more than 400 amp, that's typically where it starts making a lot of sense to parallel, right? Up to 400 amp panels, guys, you can pull them with 400 amp, 500 amp kcm. But to go to a 4,000 amp, you got to parallel. Unless you use bus stop. Okay. Any comments about how to size here? And because I know you guys are creative and you're going to accuse me of getting things from my basement, like I said, here's where it tells you in the code. And please don't make me go verify each one of them. You guys go verify at your own time. So this is where it tells you where these can summarize all the stuff for you. The most important one is table 250.66 because that's how we size the main bonding jumper.
You check the focus.
Huh?
Focus.
Oh, it's not focused? Was this good?
Much better.
Is it better here? No.
About the same.
Was it same?
Not too bad.
No. So
Yeah.
Can we go home and call it a day, huh? Wow. That's good. That's better. Sorry, guys. I keep moving here and probably not saying it. Okay. So everybody kind of going to give me a pass on these. You're not going to go check it now at least. Okay, so then this is how we size it. So let's go size it. When we size, guys, the grounding conductor, I decided single-handedly, Chad, to run, instead of 11 runs here, I decided to run 10 runs of 600 kcm. Can I do that? 10 instead of 11. Remember I said 11, 500. I can run 10, 600. If you do the math on how much amp, you can carry a switchgear 4000 amp with 10 runs of 600 kcm. Okay, this is how MPG or J is main bonding jumper. The way we size a main bonding jumper, you take the number of sets in parallel, multiply them by the size of the service conductors, right? And then multiply them by this magic number, 12.5%. Cool? So if you do that, you end up with 750 kcm. If you don't know if 750 kcm is a standard conductor or not, right? Some of it, you might not know if it's a conductor. Where are you going to go? Chapter 9, Table 8. If you guys go there, which is so all of you are masters, pass the journeyman master, you know where Chapter 9, Table 8, you're going to find 750. So that, your neutral is going to be, in this case, your main bonding jumper is going to be 750. Your main bonding jumper is going to be 750. Your main bonding jumper. Now, if you take the 750, guys, divided by 10, why did I divide it by 10? I have 10 runs, right? Divide this by 10, get you 75 kcm, right? You take the 75 kcm, take it to chapter 9, it gets you which number? 1. What's wrong with number 1?
Too small.
Not too small. You can't parallel it. So not too small. You cannot parallel it. So you have to go to 1 knot. Now, I know some of you guys have looked at my service are 600 amp and my neutral is 1 knot. A lot of engineers, guys, they go, if the service is one size, we go 2, 3 sizes and we size it and call it a day. But remember, this is the minimum size that you can pull. Can I go higher than that? Be my guest. That's your minimum size that you can pull. And I know a lot of engineers who take 600 amp, 600 kcm, 500. We have 400. Probably they will size it for 350, kind of half of what the service is, and call it a day, 350. But that's, remember, we're going by the bare minimum. Any comments, guys? Any questions? So that's the size of my neutral. That's the size of my neutral.
Neutral's got to be in each conduit.
Yes, thank you. When you parallel. Yep. When you parallel conductors, so each conduit is going to be carrying, in this case, 4 conductors, 3-phase and a neutral. The 3-phase will be 600 kcm, and the neutral will be 1 knot minimum, but you can go higher than that if you want to. Any comment, guys, about sizing this? Sizing it? Okay, let's go to so that's my neutral. Why do we care about the neutral when we talk about grounding? Anybody, did you guys ask me, why are you talking about neutral when we talk about grounding, guys? Neutral, the code doesn't call it neutral, call it grounded conductor. It is intentionally grounded conductor. So it has to do with the grounding because it's intentionally grounded conductor. Okay, so let's go to number 1. That's the grounded. So what was the second one that I wanted to size? I'm going to go directly into, I'll give you guys a break in a second here. Let me go to number 4. Can you guys see where number 4 is? That's the conduit. All the way to number 4. Okay, here's number 4. You can see number 4 here. It says supply side bonding jumper. That's the name of it, supply side bonding jumper. That's when you take a piece of wire and you connect all the conduits coming to your service, daisy chain them, and bring them into the ground bar inside the switch. Cool? So how do you size a supply side bonding jumper? Right here, same as main bonding jumper. Same as main bonding jumper. Okay, Chad, we haven't done the main bonding jumper. Let's go look at, and if you don't believe your friend Chad, where do you go to say that? Here you go. Here's your references in the NEC code book, right here. So let's go to the main bonding jumper. So that's supply side bonding jumper. Let's go all the way up into main bonding jumper was number 2. Can you guys see that? Number 2 at the top. Okay. Let's go to number 2. Here's number 2. Main bonding jumper. Here's how we size the main bonding jumper, guys. That's when you bond your neutral. I have a 4,000 amp switch gear. I single-handedly, Chad, decided to hold 10 runs. You can do 12 or 11. So 10 runs, divide by 10, get you 400, go to 3 conduct 15 B16. She got married, changed her name lately. That's why I always remember how we used to be 3 conduct 16. Now she got married, she changed her name. So 3 conduct 15 B16. If you go there, under 75-degree column, you're going to find that you need 10 sets of 3 conductors, 600 kcm each. Remember, I'm pulling 10. You could have done 11, 500. The nice with 10 is give you kind of 5 conduits at the top, even 5 at the top, 5 at the bottom. Right? That's a better. 11 is an odd number. Might as well go 12 if you want to go there. When you place them, it's not a good idea to place them an odd number. Okay, so here's my what. So in order to size the main bonding jumper, guys, you have to size the surface conductors. We did. Right here, you're looking at it. Then the main bonding jumper, the code says you have to go 10 when you parallel. Right here, by the way, based on the surface conductor, if you parallels, then multiply the sets by the size, the surface entrance conductor size, and if the surface entrance total is larger than 100 kcm, then you have to, or copper, aluminum, God forbid, you're pulling aluminum here, and 12.5%. If it's larger than these two numbers, if it's not larger than these two numbers, what do? You go to table 250.66 directly from there. Only you multiply by 12.5% if the total is larger than these two numbers. Everybody knows that? And then you came up with 750. So my main bonding jumper and supply side bonding jumper are the same size, and both of them in this switch gear are 750. Have I said that these are the minimum? You could go ahead and do 800 if you want to, right? Do you guys parallel them? Parallel the main bonding jumper? By the way, the main bonding jumper in a switch gear is not a wire. So if somebody say, oh, shit, 750 is really hard to work with. That's because you're inside the switch gear. And the main bonding jumper inside the switch gear never ever been a wire. It's always a copper, a bus bar sized by the manufacturer based on UL. So we don't really have to mess with that. But here's what you need to mess with though, the conduits. The conduits, the manufacturers don't give you a copper bus bar to tie to conduits, do they? They don't give you that. So that basically, the main bonding jumper is done for you by the manufacturer. You might have to go, if it's a grounded system, and you have to install it or remove it. Typically installed, you have to remove it if it's not a grounded system, or if it's not a main service. Any comments, guys, about calculating too? Does it make sense? Does it make sense? And I know the system is so high, so if you can size for a 4,000 amp, a 200 amp would be nothing. You know what I mean? Any comments about number 2? So that's your main bonding jumper.
If you parallel that, let's say daisy came all together, think about it.
I don't see any. I don't know anything in the code that says you cannot parallel them. So if you cut them by half, so 750, and then size appropriately go up. I don't see anything that says, anybody know any location which says you cannot parallel a main bonding jumper. You're paralleling basically. It's not a good idea though. Then you have to have a lot of fittings though. Clamps, I guess if you have a clamp, it's not a big deal. You just land it with a clamp. But remember, you're inside in the bottom of the switch gear. Bottom of the switch gear is open. So really, the hardest thing when you're dealing with 750 is if you pull it in a conduit. Really, mainly. If you're not pulling in a conduit, you're working underground in the bottom of an open switch gear. It's not as hard as, I'm trying to say, it's not as hard as pushing it through a conduit. So. Any comments, guys? Any questions about that? And here's another. You brought very good point. If that becomes a big conductor to work with, that's where becoming, guys, bonding one conduit at a time is an alternative for this method. That's where it becomes. If you don't want to work with 750, then what do? By the way, if you don't want to work with 750, well, what's your option? This is option 1, daisy chaining. What's option 2? You know what option 2 is? You take the 600 kcm. Can somebody do it? Take the 600 kcm, you size based on the conductors in one conduit. So 600 kcm, table 250.66. Can somebody get the main bonding jumper would be in this case? Well, main bonding jumper, remember, it's not an issue. The main bonding is done as a copper bar. It's the issue becomes as a conduit. Is the conduit right here? Is number 4, the supply side bonding jumper. What was it for 600? Anybody? 250.66? Table 2.
One.
Copper.
1 aught?
1 aught for copper, right?
Over 350 through 600?
Okay.
1 aught?
1 aught copper. Okay. So instead of using a 750, daisy chain them, big wire to work with, land, torque, then you can use 1 aught from one conduit at a time. That's where it becomes an alternative. Yes, sir.
You bracket and both together.
Can we,
You bracket, mellow bracket. One through there and
using what, a wire or a
put mellow galvanized bracket and then clamp each conduit.
clamps? You can clamp them, and you have like a copper bracket.
Mellow bracket.
Yeah.
From conduit 1 to conduit 11.
As long as it's approved for bonding. Anybody does it this way? You have like a copper bar, I assume, and bonding from one to another. The lugs have to be rated for that too, the grounding lugs and grounding clamp and all this stuff. Anybody does it this way, like a copper bar go across all of them? I don't know if there's an approved fitting for it. It could, if you find an approved, UL approved fittings that bond them all with one copper bar. I don't see why not, and take them all the way as a bar, but the problem is the fittings. Okay, any comments, guys? Any comments, any questions about a supply side bonding jumper? Supply side bonding jumper. Do you guys want a 5 minutes break before we move on? Okay, let's take 5 minutes. Okay, so notoriously famous 250.66, that's what we were, guys. The system that we were sizing is over 350 through 600 will get you 1 aught copper or 3 aught aluminum. I'm sure if you're a journeyman and master, you have seen this enough in your life, right? So I just flashed this one here. Okay, so I'm trying to go online, but I can't, it seems. They keep kicking me. All right, so I'm going to go, guys, to number 3. So I'm just kind of picking up certain, so we talked about number 1, we talked about number 2, we talked about number 3 and number 4, right? The terminology is very important. The sheet that I gave you guys, I hope it summarized the whole thing. Believe me, I'm like you, I got very confused. I grew up in Jerusalem, and we don't even call the grounding, it's earthing. So if you're confused, I was more confused even. So the only thing that unconfused me when I put everything together and go to the code and put the whole big picture, it makes, at least to me, and the terminology that they use, then it makes things at least look clearer. Because if you go through the book that we have, it's really hard to put the whole picture together. It really is. Okay, so that's, I hope you guys appreciate that one. Here's the number 3. I want to go to number 3. Number 3 is called grounding electrode conductor. By code, you have to provide at least 1 grounding electrode system, at least. But if that grounding electrode system was a pipe, a water pipe, you have to supplement it. If it was a rod, you have to supplement it by another. So that's why we end up with 2 anyway. But at least if you have concrete encased electrode, you can get away with 1 concrete encased electrode. I don't know of any engineering firm or any contractor who does do one. But also the code says, guys, you only need 1. But if others exist, you must bond to them. So like catch-22. So if you have a water and you have a concrete encased electrode, foundations of a building, tied to the foundation, based on the code, you're done because you have 1, but you have to bond to the water. Well, guess what? Now the water becomes your grounding electrode conductor. So you only need 1, but if others exist, you must bond to them. Everybody understand how the whole system, that's why in dwelling we end up with what? 2, right? The water pipe coming into the building and a ground rod. If you don't have a water pipe, you have to drive 2 ground rods or 1 ground rod and a plate. You have to have 2 sources. If it's a rod, it needs to be supplemented. We don't depend on a rod by themselves. Okay, everybody understand the terminology with that? Okay, so let's go to number 4. Number 4 is called the grounding electrode conductor. I'm going to find a grounding electrode conductor for a building, a 4,000 amp switchgear. It could be 200 amp switchgear for panel. So if you guys go all the way to the bottom, all the way to 4, will you? Okay, 4. So 4, I have a few things for you for 4. Not 4, it was 3, I'm sorry. It was 3, all the way to 3. Okay, 3 has a few of them, guys. So what I did, I summarized grounding electrode conductor, GEC, at the only, typically, well, not only. typically 90% of, you're going to see it only at this, typically at the service 90% of the time. We're going to see it somewhere else too. Okay, so here's my grounding electrode conductor. Grounding electrode conductor at the main, right at the main one, that's the one the one that's going into the switch gear. The main is the one that goes to the switch gear. You do the same thing, guys. Remember that magic number multiplication? Do the whole multiplication. You end up with 6,000 kcm, go to 250.66, and you do not need to go larger than 3 aught. Does that make sense? No matter what you do, you don't have to go larger than 3 aught. Now, a lot of engineering firms, guys, they go bigger. They go 250 kcm and 300 kcm. But minimum, you do not need more than 3 aught going into the switch gear.
Why would they go bigger?
Very good point. I was hoping we wouldn't ask this one. No, good point. Here's what, well, when you have a grounding, okay, take a hospital. You need to do a grounding and bonding for a hospital. Take the electrical system for your hospital, right? That you're going to bond it. How about the data centers and all your telecommunication equipment? Need to be bonded. I don't know if you guys work with the data centers. They have their own grounding and bonding requirements. So the wires, they have
It's an isolated ground wire.
isolated ground all the way come to the service.
Supplemental ground.
Yeah. So you're going to ground these two systems, and also the other part that's going to be part of your grounding system is going to be your lightning, if any. Lightning protection for the whole building could be bonded all together because it's grounding electrode system. So all this together have to provide a low impedance to the ground. A low impedance to the ground.
So once you get to zero potential, you're at zero potential, right?
Right. Except if you have a ground fault, you want to make sure first bond for zero potential. Then the grounding electrode system is when we bond. We bond and ground for two reasons. We bond to put everything at zero potentials because I don't have 120 between one leg and the other leg and current going right through me. That's a bonding. Grounding, you ground because you want to facilitate the operation of the overcurrent protection device. So there are studies, and that book goes through it, guys. Now we're getting to the detail here. There's studies that says if the further the voltage drop. Remember that voltage drop on the feeders? You have to apply the same voltage drop rules on the grounding and the equipment grounding conductor and the grounding electrode conductor. So long story short, if it's too long, the impedance of the cables might be high enough that it will not allow the overcurrent protection device to operate fast enough to trip you on a ground fault. This will be a ground fault. So that's how they always go in that one, higher. And the other higher that I've seen, if you have a medium voltage system in a building. If you have a medium voltage system in a building, then you get into the ground mesh. If you're familiar with the ground mesh, then you go higher. We were at Boston Scientific, not far away from here, right? Towards the cities. We toured, and was done by Michelle Cooley Erickson. The ground, the ground wire around the building. What do we call help me with the terminology here. The wire that we bury, ring, that's what, the ground ring, they have a 500 kcm ground ring around the building. 500 kcm. Why? Because they want to make sure it's a manufacturing, they want to make sure everything is bonded together, every mechanical equipment, every electrical equipment, for safety. So that's kind of the justification. And because the building is too big, so you will make sure that the impedance is really up to zero. My judgment, if your building is concrete, if you're building a concrete building or metal building and you have foundation in the ground, and you tie to all these foundation and you go with 3 aught in multiple locations, you're good enough. But I would not depend, honestly, I would not depend on 3 aught. Right, grab all these and bring them with 3 aught to your service. I wouldn't go there. I would go higher, coming from this point into here, probably with, in this case, 350 or even 500 kcm just to the switch gear, because that's a very major part, right? So, of your grounding electrode system. Okay, so that's kind of the runaround for answer for that one. Let me just go to 3, guys, and let me go to 3 here. So we have the main grounding electrode conductor main. Doesn't have to be more than 3. Now go to the one that goes to the rod. The code says if you are tying directly to the rod, You don't have to go more than number 6, right? So the wire that goes from the rod to the ground bar does not have to be more than number 6. True? That's directly. Again, the word does not have to be. You can go higher than that. The one that's going to the pipe does not have to be more than number 6. The one that's going to the plate does not have to be more than number 6. The concrete encased electrode does not have to be more than number 4. Does not have to be. Ground ring does not have to be number 2. But if your ground ring, like Michelle did for Boston Scientific, they have a 500 kcm around the building. If your ground ring is 500 kcm, then the wire from the ground ring into the ground bar have to be 500 kcm because they have to match. So do you guys see these one kind of the maximum? Because it's like roots. I imagine like all these are roots for the grounding electrode system. You're having different roots. And they don't have to be higher than that. They don't have to be higher than that. Okay, so that's, and what does it say? That's all in all this application here. And if you don't believe your friend Chad, you might have to go to, because you guys are doubting Thomas, right? You're going to go to basically all this materials coming from these articles. Any comments, guys? Any questions? Any comments? Any questions? So that's your grounding electrode system, the minimum. The reason why I picked these ones, just because they have minimum for them. Minimum. A lot of guys, a lot of people, they use 1/0 for all these systems anyway, tie with 1/0 for all these grounding conductors, but they make their minimum is 1/0. To the bar, to the rod, to the plate, to the concrete is 1/0. I've seen that a lot too. Any comments about this? Would you guys do it differently? So again, bare minimum, bare minimum. So that's your grounding electrode conductor. So that we covered this one, my friends, right? Number 3, we covered number 2, number 1, all this. Now I'm going to go to the easier branch. I want to branch off right here and go to a subpath. Any question about the main? So the main service, the code says the following. In the main service, you have to bond the neutral, and then like we did right here, so your neutral must be bonded to the enclosure where the circuit breaker, the main circuit breaker is located. That's what I did. We bonded here to here, and this is also bonded to the enclosure, right? You have to bond the conduit metallic into the enclosure. We did that one. You have to bring all your grounding electrode systems into the switch gear, either by grouping them and bring a one home run, or individually bring it to the switch gear. And we did that one. Any comments, any questions? Anybody does it differently? So what you looked at, what we covered right now is 2 chapters in the book. Just about the main and so forth. Okay, I'm going to take one more, now we'll go to one branch, guys. I'm going to go to this branch, and the reason why this branch I'm going to go to it, because it's easier branch. So now suppose that I have another, this branch happened to be 2000 amp, I think. I can't remember what's the, here you go. So now I have a sub panel, same building. I have 1000 amp switchboard or panel board, typically panel board, in one end of the building, and I'm taking a feeder to feed at 480. We have not created new voltage, 480, and I went to a sub panel in the second building. Now, sub panel in the second building, guys, be it in your house or be it in a building like this, be it 1000 amp or 100 amp sub panel, the grounding is identical, the same thing. Number 1, you have to provide number 6. You see that number 6? Number 6 is called equipment grounding conductor, not grounding conductor, equipment grounding conductor. So you have to pull 5 conductor cable or 5 conductors in a conduit, right? Between the 2 equipment, 5 conductors. What are the 5? The 3 phases, the neutral, and an equipment grounding conductor. Now we all know that rigid metal conduit and EMT and bunch of metallic conduits can qualify as an equipment grounding conductor, right? You can't qualify as an equipment conductor. So that conductor number 6 could be your rigid metal conduit for all practical reasons. Does that make sense? Could be your rigid metal conduit. Or if you're using PVC, let's just say we're using PVC, then you have to pull an equipment grounding conductor with it. Also, for 1000 amp switchgear, I will probably pull an equipment grounding conductor just for safety, just to make it safer. Pull an equipment grounding conductor. But remember, I'm not paying for it, and you guys are bidding it. and installing it.
If you use conduit, are you required to put a grounding bush on either end then?
Now we're getting into grounding bushing. 1 second, absolutely. That will be your number 7 here. See that number 7 here? Coming to number 7. So let's say we're having an equipment grounding conductor coming to the switchgear, landing on the ground bar in the switchgear. I have my neutral bar, the neutral bar completely isolated from the box or the frame, and the two are not tied together by code. Must not be tied together. You guys are familiar with this, right? Does that make sense for all of you? I'm repeating things that you know. Otherwise, we have to call the state about your license, right? If you go bond the neutral here, that's bad news. Okay, we'll talk about why it's bad news later on. So we bonded these together. So let me just go to number 6, guys, on size number 6. Now remember, I have a 1,000 amp feed circuit breaker sitting right here, feeding a 1,000 amp panel board. So I'm sizing for a 1,000 amp panel board, okay? So if you guys go to number 7 all the way down and see how we size that one and making it easier. I hope these numbers make sense for all of you guys, all the way to number 7. Okay, number 7 is called, number 6. Number 6. Number 6 is called an equipment grounding conductor. These are terminology from the code, EGC. It's based on overcompression device for the feeder. If feeders are paralleled, one full-size equipment ground conductor in each conduit. One full size. If you parallel, you don't cut them. I don't know, I'm sure a lot of you are familiar with that one. Your equipment ground conductor cannot be parallel. You have to pull one full size with every run. Okay, so take this example. I have a 2,000 amp panel. I want to size it. So you go to 2,000 amp, 250.122. If you guys go to 250.122, very quick, very fast, right here. And for a 2,000 amp, let's go all the way to 2,000 amp, jumping to these tables. How much did you guys come up with? I'm just going to flash. There you go. So 2,000 amp, you guys are familiar with this table. Here's my 1,000 amp. Was it 2,000 amp? 2,000. Did they size for 2,000 amp? Yeah. Did I lose it then? Oh, there's 1,000 there too. Okay, that's what I thought. What did they do? If it's 1,000, it will be 2 odd. If it's 2,000, it will be 250. Right? Everybody familiar with that table? Okay, so let's go minimize that. That's what I thought. Okay. All right. So there are multiple panels right here. I'm going to go number 6 is repeated in multiple locations. The only location I care about right now is the one that's going to 1,000 amp right here. Did we say 1,000 amp? Okay, so let's go to the 1,000 amp only. Forget about the other one. So that would be a 2 watt. Okay? So here's my, so my 1,000 amp panel will be a 2 watt, 2 watts right here. Don't look at the 2,000. We're coming to the 2,000 because number 6 is repeated somewhere else. Okay. And don't look at here because we're coming to this area. Just look right now at the 1,000 amp because that's the number 6 that I'm signing for. And here's the code references for it. Any comment, guys? Any questions? Any comment? Any questions about that? Straightforward, right? And how many of them do you have to put? As many as you have runs. So this is not just one conductor. This is a 2 watt conductor. As many runs. So if I want to parallel these, this is 1,000. Say I want to pull the 4 runs, 250 amps. So 4 runs for this 1,000 amp switch gear. Then I need 4 conductors. What's the size again? 2 watt in each one of these conduits. Cool. Everybody's okay with that? Okay. So no. If you run 3 runs, then you need 3, 1 with each. That's
okay. All the same size.
All the same size. That's the most confusing things because we don't parallel.
Yeah.
The idea.
One conduit.
Yeah, the idea, guys. Oh, now if you put them all in one conduit, do you guys do that? 3 runs. I don't know if you can find a conduit.
I think what he's saying is
The size of that wire right there would be the same no matter how many conduits you use.
Absolutely. The number will be different. Yeah. But say if you were pulling these 1,000 amp feeder in a bus duct. I can have a bus duct for 1,000 amp. Well, we don't need an equipment ground conductor, but you can only, now you need only one equipment ground conductor. If you have a cable tray, if you're pulling the feeder with one cable tray, all your parallel conductor are in one cable tray. you can put one conductor with it as equipment ground conductor, except the cable tray itself qualify as an equipment ground conductor too. So when you pull with separate conduits, you have to pull one in every conduit. Any comments, guys? Any questions about the equipment ground conductor? Okay, I'm hoping I kind of and please ignore the 2000 and 75 kVA because we're coming to them. These are different parts of the system. Okay, we got that one. Now let's go to number 7. So I'm at the second panel. I'm at the second panel, guys. I have my equipment ground conductor on both sides. Now I want to remind you, there's also, can you guys see that number 7 here going to, is 1 7 here, 1 7 here. That's bonding the conduits. If your conduit is PVC, you're done. Number 7 does not exist. If your conduit is rigid, threaded, then the bushings that you use will be tight enough, the hole matches the conduit, you're done. Because these conduits, number 7, guys, it's called equipment bonding jumper load side, right? Why load side? The number 4 was supply side bonding jumper. Here's the main, the conduit coming before the main, that's supply side bonding jumper. Here's the main, the conduit going after the main, that's called equipment bonding jumper load side. Why load side? Because it's the load side of the service. Does that make sense? The load side of the service. Who cares when you size it? If it's on the load side, you size it as an equipment grounding conductor. If it's on the line side, we change the name first. We call it supply side bonding jumper, and we size it like a main bonding jumper. That's the difference. Does that make sense? In this case, and we'll talk about the fittings in a second here. In this case, suppose I have, now remember, the bottom of the switch gear is open. So I really don't have a whole lot of option when the bottom of the switch gear is open. I'm going from underground with rigid underground all the way to this sub panel here, the 1000 amp. I need to bond that rigid, the feeder. So your option of bonding, you have to have a bonding jumper, a clamp, right? Clamp on it, a bonding jumper with a bonding fitting here with a wire that goes and tie exactly like we showed, and that wire will be sized. What's the size of the equipment that we came up with? 2 watt. It will be a 2 watt. Exactly the same. It will be a 2 watt. Now you have 2 options here. How many conduits we say they're going to be coming out of here to the 1000 amp? 4 conduits, based on my example. You're going to have 4 rigid coming from underground to the feeder. 2 options, the same thing. Daisy chain them with the 2 watt, or the same size, 2 watt, 2 home runs, 1 from every conduit into the ground bar. So I can take 1 from every conduit to the ground bar, or if I have 4 of them on this, and typically from the bottom, coming 1, 2, 3, 4 here, 1, 2, 3, 4, or daisy chain them 1, 2, 3, 4, all the way. Either way, the size is still 2 watt. Doesn't change. Any comments, any questions, guys? Unlike the supply side bonding jumper, we did change, right? It was 750 if you have 1 that daisy chain them all, and if it was 1 at a time, I can't remember what we came up with. 1 out if it was 1 at a time. Any comments about this so-called equipment bonding jumper supply side? Equipment bonding jumper supply side. And the same thing on this side, guys. It's going to be equipment bonding jumper supply side. Now here's where the issue becomes. Number 7 becomes very important to bond it if you're using the EMT conduit or the rigid as an equipment grounding conductor. If you're not using the number 6, then number 7 becomes very crucial to bond the conduit, bond it properly. Either way, you have to bond. Let me just tell you, either way, you have to bond it properly. How do you bond it properly? There are different ways of bonding, guys. You have to have bonding bushing, a wedge, bonding clamp on both sides. Because what happened here, if you have a ground fault in this system, let's just say if you have a ground fault right here, the ground fault, the current is going to go, part of the current is going to go right through the equipment grounding conductor, right, to the service. The other part is going to go through what? Through your EMT or rigid conduit. So you have to bond your EMT or rigid conduit on both sides with the proper bushings or clamps because both of them will be acting as an equivalent ground conductor under a ground fault condition, under ground fault condition. Any comments, guys? Any questions? I'm going to flash you to number 7, way at the bottom. So remember, here's number 7 is here and here on both sides of the conduit. So if you guys go all the way to number 7, and this is how it tells you. Number 7, only look at the 1000, will ya? Number 7, 1000, it says same as equivalent ground conductor. So don't even worry about it. Same as equivalent ground conductor, and it's 2 off. And where did they get this one? Again, I like to always flash the code, and here's where it tells you that's what you need to do. Any comments, guys? Any questions? Any comments? Any questions? Now, could you get away with number 7 if you have a threaded hub? You don't need it, right? Threaded hub will take care of that business for you. Could you get away with it if you have a wedge, a grounding wedge that tightened? Yep, you don't have to. The best way, obviously, is to have a grounding fittings with a jumper. That's the best way of doing it. But there are ways of getting away around having the grounding pushing with a wire. The only thing, and please help me, you guys are in the field too. The only way you have to almost use a special type of bonding for it. Now, I'm an engineer, so if this is remember, this is a 480-277. When you bond for 480-277, it's more strict than bonding and grounding for 28120, right? If it's 28120, you could get away with half an inch or like 4-inch EMP conduit with just the connector, right? Connectors that will bond the two together. If it's 480-277, you have to have a special bonding connector that have more teeth to eat into the panel. You guys have seen these ones that stand like this. When you tighten them, they eat into the panel. Better connection. Or grounding bushing with a jumper or a wedge that you put it behind the lock nut here, and you tighten it to eat into the pipe. So there's a bunch of options that you have here to bond that conduit. Any comments, guys? Any questions about bonding the conduit? Yes, sir.
You talked about doing that on both ends, right?
Both ends.
One end.
Both ends. Both ends. And the reason for both ends, guys, if you read through the requirement too, is because under a fault condition, both of them are going to be carrying equivalent ground conductor. So if you do in one end and you have a high ground fault, this is a 2000 amp switch gear, you have a ground fault 480, it pushes a lot of energy. They discovered, at least based on Soar's book, that these fittings that's not bonded properly will burn. What's wrong with them burning? You know, they could be a fire hazard under ground fault condition. Now, could it happen? You could 50 years and never happen, right? That's the problem when we size systems, guys, is we size it based on our scenario that could never happen. But we do it anyway because we size based on our scenario. Any comment, guys, about the equipment bonding jumper load side for this sub panel, the load side for this sub panel? Now, if you're using PVC, if you're coming with PVC, you don't have to worry about anything, right? All what you have to do, mechanically attach the PVC to this box. If you're coming from underground, mechanically means it will be in a concrete slab, so it's really mechanically sound. It's not shaking. If this is coming to a panel, you have to have the fittings to attach it mechanically to the panel. Any comments? Any questions, guys? Anybody disagree? This is my understanding, especially the equivalent bonding jumper, guys. Anybody has a different way, different interpretation? So that's basically my bonding and grounding at the sub panel. Any comments about the bonding and grounding at the sub panel? Equivalent grounding conductor, I bond the conduit if it's metallic from both ends with the proper fittings. Definitely, when you guys bond, they tell you if you have knockouts, that's a big deal. If you have a knockout, and I always call it, if the conduit match the hole, then that's one bonding and grounding. If the conduit does not match the hole, means you have knockouts, you have half an inch, and you just got rid of the half an inch and you butch half an inch. Then, if your system is 480-277, you have to bond slightly different, either by having fittings that eat proper fittings that tie to the panel, or a wedge that you install it to bond the pipe, it's 480 to 77. If it's 28120, it's not a big deal. That's for the equipment bonding the pipe for the equipment. Any comments, guys? Any questions about this sub panel? That could be the panel in your garage, detached, or actually attached garage. In this case, an attached garage. That could be a 60 amp panel or a 100 amp panel in your garage. Same thing. Any comments, guys, about this? Does it make sense? No? Yes? Okay. Let's go to another panel this time. That panel is going to be in a different building. That's your detached garage, your shed, or your 25,000 square foot other building on your campus, right? That's what we do. If you have a campus, guys, you have typically one service coming to a building, and you shoot feeders from one building to another. If you're the U of M, these feeders will be 13.8. That's how they have distribution system, 13.8, and they're shooting from one to another. If you're a small campus, you're 480, and you shoot with 480 system. Now, do you have to do it this way, by the way? If you have a campus, can you have multiple services coming to your campus? You can. They're different separate buildings. They're separate buildings. Okay, so let's go to the scenario. Here's my scenario. This scenario, guys, because it's easier. Now, I went to a separate building, and I'm still pulling. I went with a 2,000 amp. This has to be switchgear in this case. 48277. Went to a separate switchboard or switchgear, and I need to do bonding and grounding. Okay. Now, number one, you have to have a 5 conductor cable if you're going underground buried cables. 5 conductor cable, or you have to have 5 conductors in a PVC conduit or rigid conduit, or you don't want to bury EMT. Rigid, treated for corrosion, or typically everybody knows the conduit of choice when we go underground is what? PVC, because of corrosion. Okay, so now just because I am pulling rigid conduit here, just because I need to bond the conduit. So I'm pulling a rigid. I have 5 conductors. You have to pull the 3 phases. The neutral, right? Your neutral has to be sized, and you also have to pull an equipment ground conductor. Now the equipment ground conductor the same way, except you're going to size it now for 600 for 2,000 amp. Same size. That's why I call it number 6. No changes. It's just another sub panel. The number 7, guys, is that also the equipment bonding jumper load side, same size. Same size, meaning the same process, except it's going to be sized for 2,000 amp. And what's the size, guys, that we came up with 2,000 amp for that? 250. How much? 250. That will be 250. So this will be a 250. This will be a 250. Now, number 6, guys, there will be a conductor in every set of conduits, right? Because 2,000 amp, you typically divide them. So we have 2,000 amp, divide by 5 will give you 400, right? Right? 2,005, 400. You pull. You can pull 600 runs here. 600 runs. So how many? 4 conductors, 4 sets of 600, or 5 sets of 600. Okay, so then these 5 sets, you need to pull 1 conductor in every set. If it's EMT, or if it's rigid, or if it's PVC. Except if it's PVC, you must do that. If it's EMT or rigid, you don't have to do that. You can depend on your rigid or EMT as your equipment grounding conductor. And being an engineer, I really don't like to depend on rigid at this amp, at this voltage, to be my only equipment grounding conductor. So, okay, so that's we size it. Then, the only difference in the second building, guys, the code says you have to establish new grounding electrode system at the second building. That's different, right? You have to have a new grounding electrode system. It could be, because it's a big system, I have a grounding bar here, copper bar, in the switchgear room. At the same thing, I have to go to my water pipe, I have to go to my rod, to steel, to the wire, the ring, into the plate. All your grounding electrode systems and the second building that exists must be bonded to. But how many do you need? You only need 1. You only need 1. Except if that one was a pipe, a water pipe, or a ground rod pipe, or a ground rod, then you have to supplement it by another one. That's why we end up, guys, most of the time with two, water and ground rods in the second building at least. If your building is a concrete building, then you tie to the rebar if you have access to it. So you really do the grounding electrode system exactly as if it's a new service. Same thing, as if it's a new service. The only thing you don't do, can you guys see the bonding between the neutral and the ground? No bonding between the neutral and the ground. So the only thing you don't do, exactly like a service. Any comments, any questions? The other thing different in the second building is number 7 here. In the service, it's called supply side bonding jumper because a supply side of the service. Here, it's equipment bonding jumper load side. Why? Because it's the load side of the service. Disconnect means the fuse, the circuit breaker. Any comment here about this? Does it make sense? Yes, sir.
Yeah, the second building, you have to always bring the ground over. You couldn't get a separately derived system on the second building if you had all your,
You cannot feed your building from a separately derived system.
say you didn't bring your grounds over and you ground, try to neutral and bond it to neutral.
You have to bring your grounding
Right.
equipment grounding conductor to the second building. And you have to bond your equipment grounding conductor to the grounding electrode system. Right here. Here's my equipment grounding conductor coming to the ground bar and tied to the grounding electrode system via a grounding electrode conductor. What you don't do is you don't bond the neutral and the grounding bar together. I don't know why you say separated derived system. Separated derived system, the only time you use the word separated derived system is if you have a generator, if you have another transformer, or if you have a UPS system, or if you have a photovoltaic system. These are the terms, the separated derived system. If you feed another building from the same voltage, that's not a separated derived system. Am I getting into? See, always, that's not a separated derived system. Can I feed the second building from a separated derived system? Yeah, I can throw a transformer, indoor or outdoor, and transfer the voltage to a 28120 and feed the second building. Then that will change the game slightly, and that will put us into a separated derived system, bonding and grounding, which I'm going to talk about in a second. Yes, sir.
What if you came out of your CT cabinet and went to that second building? Then you would not need that ground?
That's a new service.
It would be the same.
That's a new service. That's completely new.
Then you don't need.
Then you don't need the equivalent ground conductor. Absolutely. You're not feeding from a switch here. You separated from the CT cabinet. You took two services. One to this building. One that's new service. Exactly. The same. Start applying the rule of the 4,000 amp switch gear on it. Nothing really changes other than here's what really changed. You just want to bond the neutral on the ground here. In this case. Any comments, guys? Any questions? Does that make sense to all? Yes, sir.
Bond the neutral ground separately when you put.
In the old days, in the old days, because to save copper on the farms, they used to bond the neutral. And now there's an exception in the code that tells you for existing building that there is no metallic connection between the two buildings. Only existing, no metallic connection, even a coaxial shield of a cable, because that could be carrying neutral current, you can get away with 4 conductors instead of 5 conductors cable here. But that's an exception to the rule, not the rule though. You're absolutely right. Then you can bond the two together. The idea, guys, if you bond here, everybody knows why we don't bond. If you bond here, then your EMP conduit start carrying neutral current. Under normal operating condition, your EMP conduit or rigid is carrying current. So it's good in Minnesota because it heats it up and it keeps warm, right? But the idea is a hazard, right? The hazard is now your conduits are carrying current under normal operating condition. Conduit shall not carry current except under abnormal condition. What's the abnormal condition? Ground faults. Ground faults. That's all. Now you could do that and bond in here and live for it forever, and then nothing could happen. But the challenge here is if you have a shield. Here's where, say if you have coaxial cable, and you bond. If you have a coaxial cable between the two buildings, every time you enter from chapter 9, every time you enter with a coaxial cable into a building, you have to bond the shield into the building, right at the point, the demarcation point. Now, so I bonded my coaxial cable at the first building. I entered another building, what do you need to do again? You bond it again. Now you shield, the coaxial cable shield is actually a neutral conductor, right? If you bond the neutral here. So there will be current going through the shield. Now that would be a hazard. Does that make sense, guys? Why we don't bond the neutral again? The code says on the load side of the service disconnect means you cannot bond at all, with exception of separate derived system. We'll talk about this one in a second. No bonding. Any comments, guys? Any questions about this? So that's how you bond and ground a separate building. Does that make sense? Is it too simple? Am I just wasting your time, guys, or no? Paul told me you guys were so talkative yesterday with Paul.
He kept us here until 8.
He kept you here until 8? Oh.
2 hours early today.
Ouch. Ouch. Okay. Before I go to the generator, I'm going to go to my separate derived system. Let's go to the separate derived system. So now we're going to go to separate derived system. I'm going to zoom into my... Okay, like I said, a separate derived system, guys, is a name given to every time you create a neutral. You create a neutral. How do you create a neutral? The easiest way to create another neutral, you already have a neutral. The easiest way to create another neutral, if you have another transformer, right? Here's a transformer, a delta, or it could be a Y, by the way, but typically delta transformer, and Y. So now I created another neutral. I call it white. That's a white neutral. That's my 28120, typically industry standard color code, right? And I pulled the 28120 black, red, blue, and I colored them because they're 28120. You guys are familiar with, if you have two systems, these are typical color code, not code requirement, by the way. A lot of people think it's code requirement, but typical industry standard color coding. The only code requirement, by the way, is if you put the 208 system and the 480 system in the same conduit or box, now you have to separate them by system and by phase and by neutral. So only time you have to separate them. So a lot of us guys separate them anyway, and you have to have a label on every panel to tell you what the color code for every system. Safety. The last thing you want to do is to take a phase of 208 and tie it to a neutral from 480 or vice versa and get you a weird voltage, high voltage that can burn equivalent. Okay, so that's very, very important here. So here's my separated derived system. I have a transformer delta Y, I create neutral. Another time you create a separate derived system, if you have a generator. If you have a generator, now I generate 3-phase. If I need a second voltage, typically we need 480, but I need a 277, so you create a neutral. Now we create a neutral. When you create a neutral in generator, you have option though. You can tie your neutral that you created to the service and call it a day. That will be non-separate derived system. The other method is I want to break the neutral, the two neutrals from together, break them, and then that will be a separate derived system. And we'll talk about the advantage and disadvantage when we reach them. Okay, in transformer, you really have no option. You have no option of tying this neutral to the neutral here. No option. You cannot tie them. Like you asked me, you can't tie this neutral and this neutral. These are apples and oranges. You can't tie the two neutrals together. So you really have no option other than becoming a separate derived system. Another place, guys, is UPS system. Uninterruptible power supply, you can run it as a separate derived system. Solar photovoltaic system with the inverters. So every time you create a power system, you have the option of separate derived system. Okay, now in this case, the notoriously famous that all of us deal with is a transformer. Because in the US, we burn receptacles at 120, right? So we have to have another transformer in most of the commercial industrial buildings. Okay, here's my transformer. Right inside the transformer, you're going to have a ground bar and a neutral, or the XO point of the transformer. Now here, we created a new neutral, and I have no choice. I have no option to tie the neutrals together because I have two voltage systems. It's not the same voltage, so you have to bond your neutral to the ground. Every time you create a new neutral, you have to bond the new neutral to the ground. Why do we do that? Why do you bond the neutral to the ground? Why can't we not bond it? Even in the service, why do we bond the neutral to the ground? What happens in the three-phase system if you lose your neutral? Say you have a service coming to your building, guys, and Excel is giving you 4 conductors, 3-phase and neutral, and there was a storm, if it's coming overhead, or accidentally the lugs on the neutral got loose and you lost your neutral. Now you're pulling three-phase conductor inside your building without a neutral, and your neutral is not grounded. You get into what we call a floating neutral, right? Floating neutral. If you have been in a building where the voltage goes up and down, right, and it dims and all this good stuff, you're looking at floating neutral. So any load that's tied between the phases and the neutral starts sharing these voltage based on how fat they are, what their impedance. The biggest load will take more voltage. So you're dealing with open neutral, and when you deal with open neutral, you burn equivalents. So one of the most important things about bonding is the neutral to the ground is stabilizing the neutral to the ground, and upon the loss of the neutral from a cell, or in this case upon the loss of the neutral, in this case you highly unlikely going to lose it here. But at the service, if you lose it, now the ground will act as your neutral back to the service. At least you don't burn equivalent. It's not recognized as a return path, but it's enough to not burn equivalents. So there's stories, guys, in residential, especially if you lose, when they give you 3 wires, right? A storm comes and you lose 1 wire, and that happened to be the neutral. And you're not bonded to the ground. Now everything in your house, your plasma TV, and your freezer are sharing 240. When that happens, you burn equipment. Anybody open and neutral and did that? I have one. Everybody has a story about open neutral. Yes, sir. What if I didn't hear? Detached building. You're absolutely right. You're absolutely right. A very good point. The same token, Chad, could apply to your separately derived building right here. What happened if I lost the neutral coming to the building here in the separately derived system? You're going to burn equivalent. Yeah. But I see your point though. But that's why here's an alternative for you though. Here's a solution for this. The solution would be to feed the building from a different service, if it's a bigger building, you can have a different service coming to it. Like who said that you come from the termination box and you go see CT cabinet and you tap it. That will solve the problem. Because the hazard, guys, from bonding here is more than from not bonding. There's hazard from bonding and not bonding. If you bond the neutral here, you create more hazard than not bonding it. Okay, so that's where we bond them. So let's go to the neutral. We bonded the neutral. Now, okay, so I'm coming here. I call this number 5, guys. It's really a main bonding jumper, except because to distinguish it from the service, they call it system bonding jumper. For all practical reasons, the way they size it, it is exactly like a main bonding jumper, except the name is different. It's system bonding jumper. Okay, so system bonding jumper. And can you guys see that little conductor number 7 here? Now I have okay, so let's just look at number 5. If you guys go to number 5, all the way down, that's called, number 5 is called what? System bonding jumper. Okay, here's my system bonding jumper. It's called system bonding jumper by the code for separately derived system. For the transformer, it's based on the separately derived system conductors, exactly like the service. Instead of basing them on the service conductors coming to the service entrance, now we sit and we base it based on the conductors coming out of the transformer. If I have a transformer, and if you parallel them, you have to multiply by the set, and also you have to apply the 12.5%. So for all practical reasons, you're really sizing a main bonding jumper, right? With a different name. That's it. No difference really in the arena. Okay, here's my here's my transformer. I size a transformer, guys, and I tied my transformer to a panel of 225 amp. I decided that the transformer is going to be tied to a 225 amp panel. If you guys go size the feeders out of to feed a 225 amp panel, what do you get? 4-aught. So my feeders coming out of the transformer to the panel, 225 amp panel is 4-aught. So you take the 4-aught now to 250.66. What's the main bonding? The system bonding jumper is number 2. That's how we size it. The system bonding jumper. Now, if you, so that's, don't look at the generator. We're coming to the generator. Just because the generator is also another. Look at just the transformer now. That for the transformer, the system bonding jumper based on a conductor of 4 coming out of the transformer, landing in the panel, the I size, and I size the transformer to match. I have a number 2, minimum. Any comments, guys? Any questions? Any comments about that? Any comments? So that's my system, so-called system bonding jumper. And if you guys okay, go all the way. So what I did here is I have a transformer, 75 kVA, typical transformer, and I'm landing it in a panel, 225 amp panel, typical, and the panel is 28120, and my phase conductor, the 208 3-phase are 4 and then where was the main bonding jumper? The main bonding jumper, I made my main bonding jumper inside the transformer, which I have the option. If you have a separate derived system transformer, guys, you have the option. You can either do the main bonding jumper inside the transformer and pull a neutral, then you don't bond it in this panel, or you can do your bonding inside this panel, but you can't do it on the neutral. Typically what they do, the best way to do it is inside the transformer. We do have access to the transformer though, right? That's our transformer. We own and operate and we bought. So typically you go to the XO here and you tie it to the ground right here and you get yourself, what was number 2 here? That was number 2 based on the conductors coming out of the transformer. Not coming in. A lot of people go size it sometimes based on the conductors coming in. No, these are based on the conductors coming out. Any comments, guys? Any questions about that? I created my neutral.
What if you're feeding like 3 different panels coming out of that panel?
What if you're feeding 3 different panels coming out of the transformer? Then it has to be, and you're bonding inside the transformer, then it has to be based on all the feeders that are feeding all these transformers. Or you bond inside the panel, and then you don't have to worry about that. So if there's 3 panels, 250, 225. So I have 4 Add the 3 4 together. How do you add 4 together? You have to convert them into KCM, and then add them all together, and then you size the main bonding jumper. Or you go directly into each one of these panels and you bond inside the panel. Then you don't have to go higher than number 2. Okay, so we got these guys. We got that number 2 here. Any comments? Any questions about the number 5, which is system bonding jumper? System bonding jumper. Now there's 2 things I want to pinpoint. Now from the transformer into the panel, you also have to have a neutral. Can you guys see that white conductor, the neutral conductor? That's white conductor. How do you size that conductor? A lot of us guys in a 225 amp panel, what do? Full neutral, which is a very good idea. Why? Because you're dealing with lighting receptacle panels, harmonics, full neutral. But what's your minimum though? Here's what your minimum is. So if you go to 1.1 here, 1.1, can you guys see that? Grounded conductor neutral at the separated derived system. Secondary, you size it based on secondary ungrounded conductor. Here's the 4 that we size. System bonding jumper is number 2. Then the grounded conductor cannot be less than the system bonding jumper. Does that sound familiar? Isn't that what we did with the main? Like with the main bonding jumper? Identical. But typically what I wrote here, guys, 4 is based on the load. Typically at this level of voltage, I always, when I do sizing, I say if you have 300 amp or less, full neutral. Because we have a lot of lighting panels and receptacle panels, and almost all of them have harmonic loads, right? And they also have a lot of loads. Now you go higher than 300 amps, most likely you're dealing with air handling units and chillers and all this good stuff. Then you start derating. The code allows us guys to derate anything higher than 200 amp, right? And neutral load, you start cutting it by 70%. So I always say 300 amp full neutral is a very good idea design-wise. Higher than that, I don't know how you guys do. Derate, you derate it. And how do you derate it? If it's a service, your minimum will be the main bonding jumper. If you want to derate it, the way I do, like if I have a 600 amp panel, take the 600 amp panel, the first 200 leave them alone, right? Anything higher than 600 amp panel, then cut it by 70%, right? That's neutral load and size your conductor, your neutral conductors. If it's not a separately derived system, or if it's not service, because a separately derived system and service, you have the main bonding jumper and the system bonding jumper to play with. But if it was just a sub panel, like a 2000 amp sub panel, how do you size a neutral for a 2000 amp sub panel? You don't have a main bonding jumper there, right? To worry about, or system bonding jumper. So I typically take the 200 amp based on 220.61, I believe. Leave them alone. Anything higher than that, cut it by 70%, add them up, and size your neutral appropriately. And if you're paralleling, you can't go less than what? 1 out anyway. Okay, so that's where we size our neutral for the separate derived system. Again, minimum is 2, but it's a very good idea is to pull full neutral. Do you guys pull full neutral with these 225 amp? Full neutral, because of harmonics and because a bunch of other things. Okay, so but we talked about the minimum. So I have my let's look at the transformer, guys, and then we'll get into the primary of the transformer. So we got these, we got the neutral. On the primary side of the transformer, you have to pull an equipment grounding conductor. Did we label it here? And number 6. Can you guys see that? Number 6, equipment grounding conductor. Number 6, you have to pull an equipment grounding conductor, right? Between the transformer, between the main panel and the transformer. And you also have to bond the bushings, if it's rigid, if it's not PVC, on both sides. That would be number 7. And did we size guys number 6 and number 7? Yep, number 6, the equipment grounding conductor will be sized based on the overcome protection device that protect that transformer right here. Whatever, I think I have a size for that. And also number 7 will be the same size as number 6. The same size as number 6. Equipment bonding jumper, supply side. Both of them, guys. Number 7 is equipment bonding jumper, supply side. I'm sorry, load side, because here's the circuit breaker, main. Everything down here, anywhere, is load side. Any comment, guys, about 7, number 7, and number 6 here for the separate derived system? Identical, like any other path.
6 can be your conduit again.
6 can be number 6 can be a conduit, but typically with transformer, because of vibration, what do we do at the end? Don't you guys flex them? When you flex them, then you can't depend on the flex. As that's the problem with transformers. When you flex the transformer, you can't depend on the flex. Is not an approved equipment ground conductor. So you will almost always end up with an equipment ground conductor on both sides.
Put a junction box in between there. You have to put the bonding bushings and bond everything.
You have to bond. Yeah, you have to bonding bushings now. The challenge. Okay, so we know we have to pull an equipment ground conductor because what do? We are using almost always. Do you guys rigid to a transformer? Do you bring rigid to a transformer? These typically flexible metallic conduit for vibration, and you pull an equipment ground conductor. You tie it on this side. Okay, now the flex also have to be tied, bonded. The flex, both sides have to be bonded. Now the one that's going to, that one and that one, this could be a bushing, an equipment grounding bushing. It could be a wedge. It could be a clamp. It could be the fittings. The challenge becomes more strict if you guys are using 480-277, which it is 480-277. So you have to have some type of fittings that more robust than the one that we use in 28120. I'll show you a couple of examples when we go into the details.
Where's your grounding electrode on the secondary?
We're coming in a second here. Yeah, I'm coming. If you don't
I
mind.
don't see that.
Right here.
Oh, okay, all right.
Right here. Yeah. Got it. Okay, so any question guys about the number 7? So you have to have a bonding bushing here, or because it's flex, you have to have some type of attaching the flex into your system. And then, thank you brought a very good point. So we bonded the flex here from both sides. Then we have to go, my neutrals bonded to the ground. Then by code, you have to take equipment grounding conductor. Can you guys see that? A grounding electrode conductor. You take it all the way and you tie it to the ground bar. Now we'll talk about this. Huh? You don't have to. You're absolutely right. So now, but I want to emphasize, now you create a new neutral, you bonded the neutral to the ground bar, and you have to go ground the ground bar of the transformer into the grounding electrode system inside your building. You have two options. Option number one is to take that conductor all the way to the ground bar if it's close proximity. That's easy, right? Option number two, if your building is a steel building, bonded steel building from all sides, the code allow you to go just tie it to the steel from one side, and then the steel, the building steel, all bonded together, will act as a bonding conductor to bring your grounding equipment, grounding electrode conductor all the way to the service.
Use a full water pipe. Have a full water pipe. For electrode. Can you go to that, instead of building to the electrode?
And not going all the way back. The only, is it bonded all the way, going, the steel is going all the way, the water pipe, it's already bonded to the service.
The plumber doesn't.
Yeah.
Up the fitting.
Yeah, see, that's the reliability. The problem is, how can you prove, if I'm an inspector, say, how can you prove that this is a reliable grounding electrode system?
Well, I don't, I'm not saying it's a good idea, I'm just
Yeah.
saying it doesn't code allow it.
I don't think so. I don't think so. I haven't seen it allowed, so it's not allowed. But the building, steel in the building is allowed in 2011. So you really, that's why I say this is the most common practice, unless you have a steel building, is to take a grounding electrode conductor all the way to the source of the grounding electrode system and tie it to it. Any comments, any questions? Any comments, guys, about that one? So here's my number 3.1. And I'm going to go to sizing that grounding 3.1. If you guys go to all the way to 3.1 here, we're jumping you. Okay. Here's my grounding electrode conductor. This time I'm going to use it for the transformer. I have my transformer, I have my panel, I size my conductors. So basically you size it based on the conductors coming out of the transformer. And does that sound familiar to you guys, number two? Number two. So your grounding electrode conductor at the transformer, your equipment bonding jumper on the load side at the transformer, both ends, and your system bonding jumper at the transformer end up the same size. They don't have to, but they here end up the same size. Remember, 250, the grounding electrode conductor, guys, you don't have to go higher than what? Number 3 up. Because the transformer size is small, all of them end up being the same. All of them end up being the same. The equipment bonding jumper on the load side and the equipment bonding jumper on the load side, we didn't size that one. So the main bonding jumper, and I have my main bonding jumper and the ground electrode conductor. The ground electrode conductor, main bonding jumper are the same size. Any comments, guys? Any questions? Does that make sense? Yes, sir.
Number 6 and number 3.1, I'm the same one.
Number 6.
And number 3.1.
No.
No.
Yeah. Number 6 is an equipment grounding conductor. Number 3.1 is a grounding electrode conductor. Yeah. Number 6. Let's go to size number 6. Yeah. Number 6. If you guys go to number 6, will ya? If you go to number 6, good point. Number 6 for the transformer. Just go all the way to the transformer right here. Number 6 for the transformer, guys. Now, number 6 is equipment grounding conductor for the transformer. I need to find the full load current of the transformer, 90.2, multiplied by 1.25, because that's how we size primary on the transformer. And I end up with this, with an overcomputation device 125 on my primary. The feeding the transformer from 125, I go to 250.122, and you get with number 6. Does that sound familiar to a lot of you guys? Is it too much details? No? Yes?
Yes.
Yes? A lot of details?
Second grade 3.1.
Yeah. So that's an equipment grounding conductor. But the assumption, guys, everybody understand the equipment grounding conductor, the grounding electrode conductor, the main bonding jumper, system bonding jumper. That bigger terminology, guys, you kind of have to know it. This is just putting the whole, fitting everything together.
Hold up right there. On that 1,000, on that number 6 for the 1,000 F1, that table there should say 250-122, not 66. Right there.
You're absolutely right. Equipment grounding conductor, 250 dot. Can you guys change that one? Thank you.
Yep.
I owe you a coffee. Coffee. No coffee? How about milk? No milk? Can you guys change that one? Thank you. You're absolutely right. Yeah, this should be the same thing, like 250, 122.
Oh,
Yeah, we use the 250 to 122. That's a typo. Did I size it right though? I should have sized it right. Size right, but I typed it. Thank you. Thank you. You're absolutely right. So this should be 250.122. Thank you. Good point. Okay, any comments, guys, about number 6? So we sized number 6, the equipment grounding conductor. So, okay, so coming here, my friends, I have my system bonding jumper, my equipment grounding conductor, my equipment bonding jumper load side here, and my grounding electrode conductor on the primary of the transformer, right? Very clear, right? Makes sense? Yes, no? Now we're going to go to the secondary of the transformer. I'm going to jump into the secondary of the transformer, if you don't mind me. On the secondary side of the transformer, I have my neutral, and I showed you guys how we size that neutral. I have my 3-phase 208, 120 coming in. Now this conductor here, this one, I call it 4.1 plus the main. And this is interesting. This one is really interesting. I call it 4.1. This is that bonding jumper on both sides, as well as this wire. Let's go, guys, to, can you guys see it? Typically you need that conductor. This conductor, guys, called a supply side bonding jumper. Same thing like at the service. They call it supply side bonding jumper. Very easy. Can you guys see that? This conductor here, from the transformer into the panel, in 2011, they call it supply side bonding jumper. Why supply side? Now, confusing me, Chad. Why is it supply side? Because they start, if you have a separate derived system, anything on the line side of the circuit breaker, which is mostly in the panel, is called supply side. It's like the service. Like imagine as if you have created a new service. If you have a separate derived system, you create a new service, right? You bonded, you went to the ground, and also the panel, when you bond the panel into the transformer enclosure, the two enclosures together, you have to pull an equipment grounding, you have to pull a wire between them because you're using flex. That wire is not called equipment grounding conductor. It's called supply side bonding jumper. Who cares? The question is, who cares, Chad? If it's supply side bonding jumper, how do you size supply side bonding jumper? Bigger, and based on the conductors that's coming out of the transformer. It's like, I mean, you basically, this number 4 and this number 5 are identical. A system bonding jumper and the supply side bonding jumper, identical in terms of sizing. How do we size them? We size it based on the conductor coming out. And if your conductors and 250.66, and if you're higher than 1100 kcm, what do? That magic 12.5%. Okay, so I'm going to take you guys down all the way to 4.1. Just look at 4.1 if you don't mind me. 4.1, guys, it's a supply side bonding jumper, separate derived system. And can you guys see what I said here? Same as system bonding jumper. System, not main. You see the difference? Main at the service, system at the separate derived system. Any comments, guys? Any questions about that? So what you end up doing here is you end up pulling an equipment and a supply side bonding jumper conductor, and also bonding your flex with the proper fittings into the enclosure on both sides. Yes, ma'am.
I just want to know, I'm going to start putting a lot of stuff in that column.
Huh.
Do you have no time for that, or do you want to wait a along?
What do you guys think? Are you asking a bunch of men for food here?
I was asking you. I was making fun of you.
I'm also a man. You put food in front of me, I'll leave.
I'm going to bring it into the back.
Okay.
So I'm going to need, like, where you're sitting back there, I'm going to need space back there so I can bring it, put it in there. And then you guys can-
Okay, thank you, ma'am. Okay, any comments, guys? Any questions about the grounding here? Any comment? I really would like your comments, guys, especially on bonding, the bonding bushings on the flex. Anybody, inspector? Yes, sir.
I'm gonna back up to the transformer.
Go back to the transformer.
I could have just run a 4-aught once between here and take care of business all in one. You're showing, you know,
That number 6.
combining 3.1, 6.0, and 7.0 all on one wire, and it's a 4-aught.
Okay, 7 and 6.6. Is that one?
So not bonding the building steel, what you're saying.
No, you can't do that. Not bonding to the steel. You cannot do that.
Got it.
A separated derived system, you have to, that's why we call it, it's like a new service. You have to go all the way. Now, does it work if you do it this way? I guarantee you it would. You know what I mean? For safety, they don't want the separately derived system grounding electrode to depend on the service. It goes all the way up to the grounding electrode system,
Can't it hit the steel close by though? It doesn't have to go all the way back to the bus bar, right?
Steel building, yes.
Everywhere.
Yes. A steel building, yes. But I see your point though. Can you take one and that will act as your equipment grounding conductor and your grounding electrode conductor, and right? In this case, it will be
They're all going to the same point.
yeah. It will be a grounding electrode conductor and equipment grounding conductor, because it's going all to the same point. I don't think you can get away with that. Did you guys do it? I'm curious.
No,
I'm
just looking at that.
Yeah. I see your point though. It makes a lot because it's electrically the same point. You're going electrically to the same point. Electrically, you're going to the same point. But typically, the grounding, this conductor here, it will be coming out of the transformer going. We don't put it in a conduit; it's going separate to the grounding electrode system. But I see your point though. I really do. Anybody has? I don't think you can get away with it though. Anybody have done it? Where you took one conductor, it would act as your equipment grounding conductor and your bonding conductor.
They always do us.
That's what I mean. Yeah. But there's a point to be said about that.
They
But
they look for that when they.
Yeah, they look at,
They look for that crowd.
Yeah. What they're going to tell you probably is you did not install a grounding electrode conductor, and you're depending on the equipment grounding conductor to act as the grounding electrode conductor, right? That's probably you're missing a grounding electrode conductor. You say, well, it's doing dual function. No, it's not allowed to do dual function basically. But I see the point though. Okay, so but think of it as redundancy though. If one of them, if you're to lose one, you have another path. So think of it as redundancy. Any comments, guys? Any questions? Yes, sir. This one? Yeah, it will be inside the switch gear. Then you have to pull another conductor, basically. You pull one inside the pipe and one outside the pipe. Can I put the two of them inside the pipe? Yes, but typically one inside, one outside the pipe, going to the grounding electrode system inside the switch gear, which is funny. I see your point.
But you don't have to go all the way back, it's very clear.
It,
You can pick up that system some other place.
with an approved system like a steel, a building steel, but pipe is not, a water pipe is not. Another thing, one second, if you go to the other end of the building and you put a transformer, you drive a ground rod there and you tie to it. Same building. I have a separate derived system. I went to the service in the east. In the west, I took 200 feet away, took a transformer, separate derived system. I drove a ground rod in that area, tied to it. You still need to tie that, and it's just a wood building. No steel, nothing. You still have to tie the two grounding electrode systems together. So they end up forcing you to have number 6 tying the two grounding electrode systems. Does that make sense?
You could, if you had supplemental grounding bars in closet, if that was tied back to the grounding, the main grounding bus, you could tie that transformer into that grounding bar.
If that we have supplemental grounding bars, yes. As a matter of fact, they do this all the time. What they do for risers is they take a ground, but you have requirement 3/0. It has to be 3/0. You take a 3/0 from this ground bar, and you go through the riser, through the building, to the floor to the closets, and you tab into and feed these transformers. Very commonly used. Very commonly used. But you're still going to one point, though. You're still going to one point. That's why in bigger system, guys, that bar moving it away, it's the best idea because you have a lot of things to bond to, and you don't want to put things inside the switch gear. Good point, guys. Any comments, any questions? So we went 3.1, you don't have to go all the way to the bar. If you're building steel, you tie to the steel, you're done. That's the only time you can. If you would drive a ground rod right here, you have to tie the ground rod to the other ground electrode system in your building that's not already done. So you can take a 3/0 from here, go all the way down to transformer tab feed 1, transformer 2, transformer 3, transformer 4, and go from one closet to closet. Also commonly done. Any comments, any questions, guys, about this? Comments, questions?
A lot of your data on telephone companies like to see that master ground bar on the outside of the phone, and they give some access to for their grounding purposes rather than trying to tie on to a piece of conduit.
And that will, you're absolutely right. And that will what do you call it? The inter-system bonding. That will meet the requirement of the inter-system bonding terminal that you are supposed to do for bigger systems. For smaller system is a tiny little connector. For bigger system, your telecommunication companies can directly tie. If you have a data center, they use tons of insulated grounding system. They can tie directly to this point. To do to their system. Yeah. So don't they have a backbone? Anybody that's done grounding for data centers, they have a backbone wire that goes insulated. They use 4/0, going all the way and tying all the frames of the data center equipment with 1/0. The numbers that they use is unreal. I can't remember the standard. If anybody's interested, they have a paper about it. The standard that they use is completely not NEC code book. And the idea is they want to get rid of the static accumulation of static charges on the system, because electronic equipment, data centers, are so sensitive, it could burn equipment just from the static. So they want to make sure that they have a very robust grounding system. Okay, so we got this transformer, my friends, and then that's about it. So I went into the panel. So I went into my panel with 4 conductors here in this case. I have my neutral 3-phase and my supply side bonding jumper, and I bonded flex from both sides. I do not bond again. You can't bond again. Any comments, guys? So this is typically for any transformer, 480, 277, or 600, 208, anytime you have a created neutral. Anytime you create a neutral. Any comments? Okay, I'm going to go to the last thing on this sheet, which is a generator. And then you guys will eat. Okay, so between you and the food is a generator now. Not me. So, the last baby on this sheet, I hope it's making sense for you guys. The last one is a generator. So here's my generator. I picked a big fat boy. This is 1250 kW 480 277 generator. I'm running it as separately derived system. I'm running it. You have to decide. Are you going to run a separately derived system or non-separately derived system? If you're running a separately derived system and you have an auto transfer switch, in this case, most likely you would not have an auto transfer switch at this size. You tie directly to the switch gear, right? Paralleling switch gear. Then the only difference, you have to have 4-pole, right? So you have to add a 4-pole, break the neutral. If you broke the neutral, separately derived system. If you tie all the neutral together, which you have to make this decision for the most part. If you tie the neutral, then you don't have separate drive system. In either way, though, so this happened to be a separate drive system. So I created new neutral, and when I brought these into the switchgear, guys, the way they do it in the parallel switchgear is they have 4-pole circuit breakers, and you open them. The best way, if you have a size system this size, it will have really 3-pole circuit breakers, and you don't have a separate drive system. You tie the neutral together at that size. And no auto transfer with switch. We're having a parallel switchgear, so we do the tying via a parallel switchgear. Start things and closing things through a parallel switchgear. Okay, typically a non-separate drive system. If it's separate drive system, here's what you do. Number one, does that sound familiar to you guys? We created neutral. What do you need to do for the neutral separate drive system? Bond it. That's really it. So I bonded my neutral at number 5. You guys remember number 5? We went through that one. What do we call it though? We don't call it main bonding jumper. Anybody can guess? System bonding, exactly like a transformer. System bonding jumper. How do you size it? Based on the conductors coming out of the generator. That's it. So it's main bonding jumper right in the transformer. Typically inside the transformer will be sized by the manufacturer and bonded together through copper bars here. But if you were to size it, it will be a wire based on the conductors coming out of the transformer. I have my 3-phase 480 system. I have my neutral coming out. So now I bonded here. Then what do you need to do with your generator? You need to take a grounding electrode conductor, separate drive system, a grounding electrode conductor all the way to the steel of your building, or to the grounding electrode bar for the building. And you can see that number 3.4 is going all the way back to the ground bar here. It could land also on. It could be landing also on the steel of the building because it's bonded. And then I pulled 4.2 guys. These two little things, 4.2. These are called supply side bonding jumper, believe it or not, out of all the terms. So let's go to 4.2, will you? 4.2. Okay, here's 4.2. 4.2, now remember, we're in the generator side. 4.2 is called supply side bonding jumper, separate drive generator. And how do we size it? We size it based on the same thing, system bonding jumper. And in this case, happen to be a 400 kcm, a 400 kcm. 400 kcm. So that's also a supply side bonding jumper, supply side bonding jumper. That's assuming, his assumption is, assuming that the circuit breaker is not at the generator, the circuit breaker goes right inside the switchgear. So we're pulling all the conductors from the generator, which we can, all the way to the parallel switchgear, landing it on the load terminal of the circuit breaker. Now in a case like this, that wire will be a supply side bonding jumper. Supply side bonding jumper.
Typically the breaker is in the generator.
If you put the breaker on the generator, if you don't parallel, you put a breaker on the generator. So the good point. Now you put your breaker. So if you're pulling it as paralleling switchgear, you don't put a breaker on the generator. You don't want to interrupt it anyway. You're paralleling. If you put your breaker on the generator, that's a different story. So let's. Or multiple breakers on the generator. Now you put your breaker on the generator right here. That little piece will that wire here become an equivalent grounding conductor. If you put the breaker right at the generator, your overcurrent protection device right at the generator, and now this piece becomes an equivalent grounding conductor, and you size it based on the size of the generator, the overcurrent protection device. Okay. But if you put your circuit breaker, now this scenario, because of the size, my circuit breaker is sitting right in here, inside the switchgear. This is supply side bonding jumper. The same thing, a wire side, and also guys, the conduit coming to the generator have to be bonded. Same thing, supply side bonding jumper. You put a circuit breaker like we said here, that will make this one an equivalent grounding conductor. This one an equivalent grounding conductor, and also this piece will be treated as equivalent bonding jumper load side. So these two will be the same size. If the circuit breaker is here, they're equivalent grounding conductor. If the circuit breaker is here, that will be a supply side bonding jumper. Supply side bonding jumper. Any comments, guys? Any questions? Any comments? Any questions? So you're also right. You put your circuit breaker on the generator. You go to the ATS, auto transfer switch, into your panel. Now, all what you're doing is we're taking an equivalent ground conductor between all these equipments. So that's basically what this is, guys. So we have 4.2, 1.1, the neutral coming out of the generator. Let's go to, what was it? Can you guys see the 1.1? That's the generator in neutral. So I sized that gens in neutral for you. Okay, so here's my grounded conductor for the neutral 7-drive system. Go all the way to supply side. Where's the gen? Is this? Did I do it wrong? Okay, generator. No, I did it here. That's why. I did it right here, guys. So you size the grounding conductor. You guys typically take the full load. Here's my full load amp. Well, it depends. You multiply by 1.15 if your circuit breaker is not at the generator. If your circuit breaker is not right at the generator, you multiply by 1.5 when you size conductors. So I went from this size directly into my overcomputation device is going to be right the next size here, 2000. Divide it by 4, and I came up with 5 sets of 600 kcm. My neutral conductor, guys, personally, here's what I would do. I take the 200, the first 200, remember I leave them alone. Anything higher than 200, cut it by 0.7, came up with this, divide by 5, and that's my neutral conductor size, 350. So I came up with, what's the size of the phases? The phase was 600 and my neutral 350. That's how I size my neutral conductor for the generator. So slightly lower. Can
you explain why you took 200 amps and you subtracted out 200 amps?
Because the code says, and that's really even very conservative. If you go to this one, 220.61 A, B, and C, it says, take your neutral load. If your neutral load, I think it's A or B, if your neutral load is higher than 200 amp, you can apply more derating to it, which is 70%. So the first 200 amp, don't derate, leave them alone. Anything higher than 200 amp, cut them by 0.7. That's directly from the 220.61A. Unless it's harmonic, then you can't do it. But remember, that's at a higher level. So that's, and if you do it this way, by the way, it will be, you're guaranteed, and look at that, not smaller than the supply side bonding jumper too. It cannot be, this number cannot be smaller than the supply side bonding jumper. The system bonding jumper. Whatever size you come up with here, we have, if it's separated drive system, it cannot be smaller than the system bonding jumper. And here you're guaranteed always you're higher than the system bonding jumper. Any comments, guys? Any questions about that? Do they confuse you a lot? A little bit more? Less?
All good.
All good? Okay, so I hope that's basically what I'm hoping, guys, is that one that will put the big picture together. So back into 45 here. Back into so we started with this, we end up with this, guys. I have my service, we bonded, the utility will bond the service. We come with the CT, we bond the CT to the neutral. You come to your service, you bond your conduits coming to the service, you bond your neutral, you create a grounding electrode system here. Then you go to feed all these loads, separately derived system, create a neutral, bond it. Also bond the neutral through the grounding electrode system. You have to bond the conduits in and out. And the same separately derived system. Another building, you have to create the grounding electrode system. At the generator, my friends, you have to go all the way to the grounding electrode system, and you have, if it's separately derived system, you have to bond right at the generator. Any comments, guys? Any questions? Good, bad, ugly?
Good.
Clear.
Any comments about that? Is it clear? Serious? Okay, now read 13th chapter to get there. I'm not kidding you. I know a lot of you guys know this. This is nothing new. If you're in the industry, that's nothing really not. The challenge becomes this supply side bonding jumper and the fittings and so forth.
Hey, can you sign this paper so when we show the inspector, this is a chat? So I can do it. Here's the signature.
My name is there. What do they do it differently?
No.
What do they do it different? Let me know. I mean,
Do you have the morning sign up?
Yeah, that's right.
the morning sign up. Oh, we're gonna pass the morning sign up after we eat, guys. So is this? I'm supposed to spend 4 hours on this. We spent 2 hours. Right, 3 hours now. We started at 9.
It was like 5 hours of information.
5 hours of information. I'm going to spend 1 more hour after lunch, guys, on grounding, and I'm going to flip into overcome protection device, if you don't mind. I'm just going to show you a couple of slides, talk about the advantage and disadvantage of grounded, ungrounded system. And being an engineer, of course, I love impedance grounded system, so I have to kind of stretch my muscles about impedance grounded system. Okay, shall we eat? How much time did you guys get for lunch? Half an hour?
Yeah.
Okay. All right, let's do that.
What system do they use in the trailer stuff? You're like 60 system.
Give me 1 second. Let me just.